The meeting's being live streamed. Got it. Okay. Here we go. Once we get this going, then we'll be able to get the whole thing going here. All right. Now I have feedback. Okay. All right. So I'm going to share. I'm going to get the link to that and go to post it here. There we go. Let's see. Quote. Listen on YouTube Live now. Okay, I posted that, and so maybe we'll get some people watching on YouTube. And I'm going to go back to Zoom, and we are here. Okay, I'm going to, let's see, Stacy and Eli, give them the Zoom link, and hopefully they'll join us. And we got 3 more minutes, and I think I have everything set up. So we have YouTube, we have Clubhouse, and we have Zoom. And we have some people on Zoom, but remember, if you're listening in on Clubhouse and you want to participate, ask questions, etc., you're welcome to click on the Zoom link at the top of the room and join us. If you have questions and you don't want to come on Zoom, then you can just type them in the chat on Clubhouse, and hopefully I'll see that as well. So, and let me also set up the sharing here. Put this up here. Get to that here. And go to full screen on that. Let's see, view full screen. Okay, and then share my screen. Let's see if I can do that. Share screen. And share. So now you should all be seeing, there we go. Yep. This article that we're going to be talking about today. And it's 9:58. I'm going to give it a couple more minutes because we tell everybody we start at 10, and I didn't know how long it would take. Is everybody in the Zoom room seeing things okay? And I assume you are.
Everything's fine on Zoom. Thanks.
Great.
For me. Thanks.
Great. Very good. Okay, so I think we're here. The one last thing I need to do is pull up my notes. But that doesn't work. Notes. There we go. Okay. Got some more people coming in on Zoom. And okay. There we go. It's coming. Yep, it's 9:59, so people are coming. Okay, Ben's here. And okay. All right. So welcome, everyone. Actually, I'm going to give it another minute because I want people to have a chance to join us at the beginning if that's what they were planning on doing. And we're just a minute away. Well, now it says 10 o'clock, so I get to say take a sip of tea before we get going. So let's do this. I think everything is running, so we'll find out. Welcome, everyone, to Climate Chat. I'm your host, Dan Miller. And today we are going to talk about a very recent paper that came out, I think it was last Tuesday, entitled The 2023 State of the Climate Report, Entering Uncharted Territory. This is a overview article that takes a look at the data on climate change from many different aspects and tells us how we're doing. And I'll sum it up. We're not doing well. So it's written in first of all, it's kind of a high level overview type article written in fairly plain language. It's meant for non-scientists to read it. And so today, actually, I think it's going to be a little different than we normally do. Very often what I'm doing is translating a science report into plain language. But this one's already written in plain language. So I think we'll be doing a lot more reading directly from the report and then discussing what it all means, because it has implications for everyone in the audience and everyone not in the audience. And if you have children, it has a direct impact on all your children and their lives going forward. This is not just some thing about black holes or something like that. That's a really interesting scientific thing, but probably won't have much impact on you personally, unless a black hole flies through the Earth sometime or something like that. This one is all about what we're doing to the climate, how it's changing, how fast it's changing, and the implications for that. So with that, I think we'll dive in. First, a few notes. Leon Simons here. I think you can see my pointer when I move it. Leon Simons is one of the co-authors. We've interviewed Leon several times here on Clubhouse and on Climate Chat, and he might join us again today. So it'll be great if he does. I said any amount of time that he has. William Ripple's the lead author. I asked Leon to invite him. I don't know what happened there, but I will make one note that Leon told me about yesterday, and that is that Saleemul Huq, I don't know how I'm pronouncing that right. He just passed away like 2 days ago. And it was a shock to everyone. So Leon was really shocked that he passed away, one of his co-authors on this paper. So we send our condolences to his family. And he worked tirelessly. I didn't know him beforehand, but I read up on him because he's on Twitter a lot now because he died. And he fights for like climate justice, getting the wealthy nations, to pay damages to poor nations and things like that. So he will be missed. And I see Stacy is here. I'm gonna find you. Let's see, how does that work?
I am here.
Yes. Oh, there you are. Ah. Okay, I'm going to make you a co-host so you can let people in the room when you see them. And by the way, I will say we are doing an experiment today in that I posted this Zoom link on Twitter, which meant anyone can see it. Anyone can try to get into the room. And Twitter and Zoom sent me a warning notice that I had done that, which I did on purpose, warning that we could get all kinds of people joining the room to disrupt the room. We'll see. But if that happens, Stacy, you can kick them out. So.
Yep. I'll be on the trigger. I have an itchy trigger finger. Yeah.
And I don't see the list of people quite as clearly as I do on Clubhouse. So if you see Leon Simons join, could you make him a co-host and then, alert me to that?
I will do all that is in my power. Yes.
And I also, if Eli joins, you can make him a co-host as well. I think co-hosts can make people. Oh, there he is.
Oh, here he is.
There he is. So you saw that. All right. So let's get back to the paper. Now that we got some of that out of the way. So I'm just going to read the abstract, which is very straightforward. Again, this is written in plain language. And again, the title of the paper is the 2023 State of the Climate Report, Entering Uncharted Territory. They did previous versions of this, and actually had, I think, many thousands of scientists sign up to declare that it's a climate emergency. And by the way, Stacey, you can turn on the AI thing, which does the note summary. I don't remember exactly where that is, but that actually is pretty useful.
Yeah, I think I just did.
I think you did too, because I just got a little note. I wasn't 100% sure. So, anyways, this is the article, and let me put a link to the article into Club Deck before we get going here. So this is the article in the chat there. I'm going to put it in the chat in Zoom. How do I do that? Let's see. It's up at the top. Chat. Here is the link in the chat there. I guess I could do it in YouTube, but I don't. I'm balancing too many things here. So let's get back to. By the way, do you see Club Deck right now on Zoom, Stacey, or do you see the article?
No, I see Club Deck.
Uh-oh. Okay. There we go.
Yep. Now you're good.
All right. So I got to remember that it's actually just showing whatever's on that screen. Okay, here we go. So this is the article, and this is the abstract. Life on planet Earth is under siege. We are now in uncharted territory. For several decades, scientists have consistently warned of a future marked by extreme climatic conditions because of escalating global temperatures caused by ongoing human activities that release harmful greenhouse gases into the atmosphere. Unfortunately, time is up. We are seeing the manifestation of those predictions as an alarming and unprecedented succession of climate records. We are seeing the manifestation of those predictions as an alarming and unprecedented succession of climate records are broken, causing profoundly distressing scenes of suffering to unfold. We are entering an unfamiliar domain regarding our climate crisis, a situation no one has ever witnessed firsthand in the history of humanity. In the present report, we display a diverse set of vital signs of the planet and the potential drivers of climate change and climate-related responses, first presented by Ripple and Wolf and colleagues in 2020, who declared a climate emergency, now with more than 15,000 scientist signatories. The trends reveal new all-time climate-related records and deeply concerning patterns of climate-related disasters. At the same time, we report minimal progress by humanity in combating climate change. Given these distressing developments, our goal is to communicate climate facts and policy recommendations to scientists, policymakers, and the public. It is the moral duty of us scientists and our institutions to clearly alert humanity of any potential existential threat and to show leadership in taking action. This report is part of our series of concise and easily accessible yearly updates on the state of the climate crisis. Well, let's just pause and catch our breath there for a moment on that. That is pretty clear. And of course, the rest of the paper goes into the details of this. And it's quite alarming. And people say, oh, you're an alarmist. Well, yeah, certainly if you're not alarmed, you're not paying attention, I think is what goes on there. But let's just kind of, rather than dwell on that, the overview, let's just dig in and talk about the data that they present. So this is the first section titled Climate-Related All-Time Records. In 2023, we witnessed an extraordinary series of climate-related records being broken around the world. The rapid pace of change has surprised scientists and caused concern about the dangers of extreme weather, risky climate feedback loops, and the approach of damaging tipping points sooner than expected. This year, exceptional heat waves have swept across the world, leading to record high temperatures. The oceans have been historically warm, with global and North Atlantic sea surface temperatures both breaking records and unprecedented low levels of sea ice surrounding Antarctica. In addition, June and through August of this year was the warmest period ever recorded, and in early July, we witnessed Earth's highest global daily average surface temperature ever measured, possibly the warmest temperature on Earth over the past 100,000 years. It is a sign that we have pushed our planetary systems into dangerous instability. And then here, if you can see, you can't see this on Clubhouse, so please come over to Zoom if you want to see the figures from this paper as I talk about them. But there's 6 figures here. The first is Antarctic sea ice extent. That's the area of the sea ice. This is the ice on the ocean surrounding Antarctica. And you can see the red line is 2023. And you can see it's far, far below anything even close to what's happened in the past. On this B on this side, the upper right, global sea ice. So this one is just Antarctica. This is basically Antarctica and the Arctic. Again, record low amounts. In the middle here on the left, we see the North Atlantic Ocean sea surface temperature. And you can see it's not even close. It is just zooming ahead of any previous temperatures. Crazy. And here again on the right is the global. So all the oceans, again, crazy high levels of heat in the oceans at the surface, by the way. And then the bottom corner, world surface temperature. So this is the global temperature. The thing we always talk about, 1 degree, 1.5 up here would be 2 degrees. And you can see that ever since July, the global average temperature has been fluctuating around 1.5 C and is now about 1.7, a little hard to say C here, but maybe 1.8 C. And this is the global, this is that number we talk about. Don't go over 1.5, don't go over 2. Well, we're at 1.5 right now. And by the way, we're going to max the temperature early next year when the El Nino has a chance to really impact the temperature. So this is not as high as it's going to be. And the interesting thing is, if you look here from January, you see it was below 1.5 and now it's above. And there's a belief that by the time it gets to December over here, that the average temperature will actually be 1.5. Could be 1.4 something, but it might be 1.5 with a reasonable probability. And then next year, for certain, it's going to be above 1.5 because it's going to basically, start at this level and stay above 1.5 for most of the year. So then this last bottom right is the cumulative area burned in Canada. And you see all these previous years here got up to 5 million hectares. And already this year, it's above 15. I'll say that again. The maximum burned area up until October, I guess, in Canada in previous years was little less than 5 million hectares. And already this year, it's burned more than 15, more than 3 times as much. That's not breaking the record by a little bit. That's well, it's just crazy. That's what it is. So, all right, let's keep going. We are venturing into Uncharted.
Oh,
yeah,
sorry,
go ahead.
Dan.
Yeah.
That last measurement is the only one that gave me a little, if I'm playing devil's advocate, is there any hole you can poke in this? I think that's the only one that it's yes, this is a massive amount. I'd love to see it on because California burned, but I don't even know. I haven't done the math. In our burn years, what are we,
we're in a low burn year this year.
Yeah. I mean, in our high years, are we, how does it compare?
There are recent years, it's very similar. It's very similar. In fact, the number I kind of remember of the top 100 was it top 20? I think the top 100 fires in all of California history that we know about. 60% of the acres burned happened in, or the 60% of them happened in the last 3 years. It was like, over 100 years, most
And
of
we
the
had a
burning
3-year
happened
chunk.
in the last few years. I mean, yeah, these numbers are off the charts.
Yeah.
Now, not this year in California, though.
No,
Not
we got off easy. I guess it's a matter of just trying to put it in a global context. What is spin the dial, where is the fire going to be this time? And how does the burn compare on a global basis? That's the only thing that I would have said.
Oh yeah, well, yeah, okay,
context.
but they're just giving statistics here, and they're selecting things. They're going to do more.
Also, at this point, it's not the same thing, but it's.
By the way, you don't sound right, Eli. You're muffled of some kind.
It's another relevant thing with regard to wildfires. The wildfires in California last year emitted enough carbon to wipe out everything California has done to reduce its emissions.
Right, and this year, I guess, in Canada's as a country, their normal emissions, I think, is 0.67 gigatons, which is enough. This year, the wildfires have emitted a gigaton. So the wildfires have emitted more CO2 than all of Canada does by burning fossil fuels. So yeah, it's a big deal. So let's keep going here, and we are venturing into uncharted territory. Global daily mean temperatures never exceeded 1.5 degrees Celsius above pre-industrial levels prior to 2000, and have only occasionally exceeded that number since then. However, 2023 has already seen 38 days with global average temperatures above 1.5 C by 12th of September, when they stopped gathering data for this paper, more than any other year, and the total may continue to rise, which it has. Even more striking are the enormous margins by which 2023 conditions are exceeding past extremes. Similarly, on 7 July 2023, Antarctic sea ice reached its lowest daily relative extent since the advent of the satellite data, at 2.67 million square kilometers below the 1991 to 2023 average. Other variables far outside their historical ranges include the area burned by wildfires in Canada, which may indicate a tipping point into a new fire regime. And by the way, for everyone who has just recently joined us, we're discussing a new paper. It's titled The 2023 State of the Climate Report, Entering Uncharted Territory. You can see this in the links. You can see this in the links on Clubhouse and on Zoom. And by the way, if somebody wants to check to see whether the YouTube live stream is working, that'd be great, but I can't do that too. Anyway, let's get back to where we were. Anthropogenic global heating is a key driver of many of these recent extremes. However, the specific driving processes involved can be quite complex. For example, rising Atlantic Ocean temperatures may be connected to Sahel rainfall and African dust. Another potential contributor is water vapor, a greenhouse gas, injected into the stratosphere by an underwater volcano eruption. That's the Hunga-Tunga volcano. The recent rise may also be linked to a regulatory change mandating the use of low sulfur fuels in ocean shipping, because atmospheric sulfate aerosols directly scatter sunlight and cause reflective clouds to form. The sudden rise in temperatures is also likely contributed to by the onset of an El Nino event, a naturally occurring part of the climate system, which could itself be affected by climate change. In any case, as Earth's climate system transitions away from conditions associated with human thriving, such anomalies may become more frequent and could have increasingly catastrophic impacts. So let's talk a little bit about that. I mean, we've talked a lot about these issues in the past on Climate Chat. And so what they're saying is one that we haven't talked about much is the Sahel rainfall and African dust. So dust in Africa blows off the continent into the ocean, and that actually causes a lot of different effects. It affects hurricanes and the amount of CO2 uptake by the oceans, because that dust has iron in it, and that fertilizes the ocean for algae blooms. This is considered to be a very long-term climate impact worth discussing some other time. When the earth is barren and too hot, then Africa is more dusty, and then will blow more dust into the ocean, which gets more iron in the ocean, which gets more algae and plankton to grow, which takes more CO2 out of the air and cools off the earth. So it's sort of a way of like a temperature regulator for the earth in a very, very long-term sense. But it could also has like short-term impacts on temperature. That one I haven't studied, this article from Wang, which talks about that. We have talked about the Hunga Tonga volcano. Jim Hansen says some studies say it has a slight warming. Some say it has a slight cooling net effect, because not only did it put water in the atmosphere, it also put some sulfur in the atmosphere. But he said in any case, it's not a big deal anymore, because it only lasts for a year or two. So it's not an explanation for why things are so hot right now. The recent the link to ocean shipping and the new rule, International Maritime Organization rule, that said ships have to use low sulfur fuel, that we've talked about a lot. That's what Leon Simon's work is on, and that does seem to be, and Hansen agrees, it's a likely big part of the rapid warming that we've seen recently. So any questions on that? By the way, if you have a question, just under reactions is to raise hand, and then we can see that, and that would be a good way to tell whether anyone has a question or a comment on anything while you're on Zoom. And again, if you're on Clubhouse, which I'm not really monitoring, I'll take a quick look here. If you want to join the discussion on Clubhouse, then go to the Zoom link at the top of the room and join us there. And if you want, you can also put questions in the comments, but maybe someone can monitor that and let me know on Zoom whether there's any. Yeah.
Hi, Dan. This is Z. I just want to let you know, it's the first time I've joined you guys on Zoom. I usually meet you on Clubhouse. So I came from Clubhouse to here. And when I did that, it did kick me off of the app of Clubhouse. So you can't, I personally can't do both using my iPad. So I'm going to just stay here and thank you. And it's good to see everybody. Yeah, thanks.
Yeah, and if you are in Clubhouse, I do suggest you just come over to Zoom and you can hang up on Clubhouse, because once you're on Zoom, you'll be able to see all the documents I'm showing. You'll be able to ask questions. The Clubhouse link is just so everyone who just wants to sit and listen on Clubhouse can do so. It's kind of like before, except you can't come up on stage and ask your question. That's the difference once we switched over to Zoom. And again, we might try a different platform, because this one, Zoom, has its limitations, especially in managing the room. And that's why I would much rather have the sort of the controls that we have on Clubhouse to invite people to ask questions, as opposed, then you can invite the public without worrying about it. So anyway, so let's get back up. That's Club Deck showing up. So let's do this again. Okay. Here we go. Say, where did okay, we did that. Recent trends in planetary vital signs. On the basis of time series data, 20 of the 35 vital signs are now showing record extremes. As we describe below, these show how the continued pursuit of business as usual has, ironically, led to unprecedented pressure on Earth systems, resulting in many climate-related variables entering uncharted territory. So I'll mention what these are here. And you got to please note that the graphs are sized so that there's a low point and a high point at the top of the graph. So you really have to look at the numbers to really get a good feel for what these mean. It's more important that they show you the direction of what's happening. It's hard to determine, it's hard to get a feel for the absolute amounts. Human population here going up. Fertility rate, birth per woman, going down. Amount of ruminant livestock, cows, going up. Per capita meat production going up from 30 to 45 kilograms a year. World GDP going up. By the way, the beginning of this is 1980, and the ending point is like 2022, probably, where they have the last amount of data. Could be 2023. So GDP going from 25 or so up to 90 something. Global tree cover loss. So this is the loss of trees, hectares per year. So it was going up and up and up. It's gone down a bit now. I mean, well, we're still losing trees, but at a slower rate than we did, I guess, a decade ago. Brazilian rainforest loss was very high in the past, and then it was started going up again. But now with the new elections, they're taking steps, and it's just begun to drop, which is good. Energy consumption, solar and wind is going up, but oil, coal, and gas are way too high. They appear to still to be going up, while coal going down a little bit, but gas and oil still at record levels, and that actually is a big that's the problem right there in that one graph. Air transport was going up, then there was COVID, so it dropped, but it's going up again. This is passengers carried, billion passengers carried per year. Total institutional assets divested. This is actually a good one. This is the divest invest movement, and this says 40. That's incredible, but I didn't see this before. $40 trillion of assets have been pledged to not invest in coal, oil, and gas. So that's pretty good. And that started off. That was just a movement. We had the As You Sow leader here, interviewed quite a while ago. They're the ones who started that movement, and look what they did. I mean, that's a small group of people, and they ended up with incredible results there. So it shows that individuals and small groups of people can make a huge impact on climate. CO2 emissions, this is just the basic state of climate, like what's going on, what are our emissions. It dropped due to COVID, but it's back up again at a record level. That's all you really need to know about how we're doing. It's too high. It's supposed to be dropping like a rock, but it's not. So per capita CO2 emissions, tons of CO2 equivalent. That's per capita. Remember, so that's going down a little bit, but it doesn't really matter. I know. I mean, it matters. It's a useful number, but all the climate sees is the total. It doesn't see what the per capita is, right? So we have more people. Yeah, we can have less CO2 per person, but still the climate sees this number over here. It sees the total.
It's the Thanos. It's the Thanos measurement or something like that.
Is that how that, what is it? I'm not.
Thanos, the Marvel movie where
yeah.
he snaps his fingers and half the population disappears. That thing.
Well, what the climate sees is the cumulative excess, right? Not just what we're doing this year, but what we've been doing for the last 200 years.
That's true.
These are small changes in the fractional rate of change of a very large number of excess.
Yeah, and to give you an idea, this number here is this is CO2. By the way, I think this is too low, but I think this is really CO2 emissions, but it says CO2e emissions. But whatever, about 40 gigatons a year. That's versus the 2.4 trillion tons that we've already put in the atmosphere. So this is on the order of 1.5% of the total. So we add roughly speaking, 1.5–2% to the total each year. Okay. Greenhouse gas covered by carbon pricing. That's interesting, but this percent, so it's saying that about 22% of our carbon emissions now are covered by carbon pricing. I guess the number one would be the European trading scene, ETS in Europe. They have a real carbon price. In the US, we don't. We do in California. Maybe they count that as well. And there's good and bad pricing schemes. And we've talked about that before. But so that's an interesting statistic, actually. Carbon price per ton, this must be the average, getting above $20. I think in Europe it's closer to $100, so that's good. But this would be the average, which includes many places where they really have more kind of example numbers. I mean, nominal prices. Fossil fuel subsidies. This is one they talk about. We'll talk about later. Because of the Ukraine war and everything, the subsidies on fossil fuels doubled to over $1 trillion. So when people, when fossil fuel people complain about subsidies to renewables, you have to remind them that fossil fuels are like the most subsidized thing in the world. Governments that have declared a climate emergency, I guess this includes cities and towns and things like that, over 2,200. Okay. And then there's even more. And we talk about, so again, for people in Clubhouse, I'll just describe it. One is carbon dioxide, the Keeling curve, showing it going up from 1980 at around 300, maybe by 320, up to 420 now. Methane is going up to over used to be pre-industrial, about 700 parts per billion. Now it's over 1,900 parts per billion. Nitrous oxide, another powerful greenhouse gas, from 300 to over 340, I guess. Surface temperature, that's the one we were talking about there, over 1 degree now, but actually over close to 1.5. So I'm not sure what that one doesn't reflect the latest data. Earth's energy imbalance. This is how much more energy is coming into the Earth than is going out. This one is really quite shocking. It doesn't get talked about enough. But when I helped Jim Hansen with his TED Talk in 2012, not that long ago, 11 years ago, the figure he used was 0.6 watts per square meter. And now the number 0.6. And 11 years later, it's 1.5. It's actually higher than 1.5, but just when you smooth out the curve, even that's 1.5. It's actually approaching 2. Again, 11 years ago, 0.6. I don't know what to say, but that's insane. That the amount of energy that the Earth is keeping versus releasing has more than doubled in 11 years. It's not like 100 years. That's 11 years. That is absolutely crazy. Ocean heat content, how much 90% of global warming heat is stored in the ocean, and that's going up like crazy. It was in 2005, it was about 10 zettajoules, and now it's up over over 30. Oh, no, it might be over 27, 28. Wow. Ocean acidity, the ocean is taking up CO2. That makes it more acidic and dramatic. These are small numbers, but the ocean's big and they make a big difference. So from about 8.12 to 8.06 over that time frame. Sea level change, this is in millimeters. You can see it's going up quite a bit. This is so 25, like 75. That's 7 centimeters. Is that right? Something like that in a relatively short amount of time. That's a lot. We're talking about the whole world is 2/3 oceans. To raise it that much is a very hard thing to do, but we're doing it. And I will mention that Jim Hansen, in his latest newsletter, which we'll maybe cover next week, said that we could see several meters, which is like 10 plus feet of sea level rise in the next 50 to 150 years. So even though this number is small, it can accelerate upwards. Minimum sea ice. We talked about that one before, dropping dramatically. Greenland ice mass, the amount of ice on Greenland dropping by over 4,000 gigatons. Gigatons, a billion tons. Arctic mass loss, that's equivalent for Antarctica, also dropping. There was a thought that with global warming, it would snow more on Antarctica and Antarctica would gain mass. But we have satellites to actually directly measure the mass of Antarctica, and we can see that it's actually dropping, not rising. Glacier thickness dropping. Areas burned in the United States. Obviously, long-term trend going up and up and up. From it was 500,000 hectares per year, and more recently 4 million hectares a year. So dramatic change there. Global tree cover loss, so the loss of tree cover went up a lot, dropping a little bit now, but still at a very high level. $1 billion floods events per year. The long-term average, and you have to kind of average those out. So the long-term average from 1980 to 2010 was less than 1. And from 2010 to 2020, the average is over 1.5, or about 1.5. So that's a big change. Extremely hot days relative to 1961, 1990. That's going up quite a bit there. All right, I think we did enough of the graphs, especially for those people in Clubhouse who can't see them. So let's talk about energy. Again, if you have questions on Zoom, please raise your hand using reactions, raise hands. Energy. It appears the green recovery following COVID-19 that many had hoped. Oh, I'm sorry. It appears the green recovery following COVID-19 that many had hoped for has largely failed to materialize. Instead, carbon emissions have continued soaring, and fossil fuels remain dominant, with annual coal consumption reaching a near all-time high of 161.5 exajoules in 2022. Although the consumption of renewable energy, solar and wind, grew a robust 17% between 2021 and 2022, it remains roughly 15 times lower than fossil fuel energy consumption. A major driver of economic and energy trends is Russia's ongoing invasion of Ukraine, which has accelerated the transition to renewables in Europe, but which has also caused some countries to switch from Russian-supplied gas to coal. Already, this conflict has contributed to a massive 107% increase in fossil fuel subsidies from US $531 billion in 2021 to US $1.1 trillion in 2022 because of rising energy prices. Although these subsidies may partially protect consumers from price increases, they are often not well targeted and help promote fossil fuel related energy use and profits over low carbon alternatives. So now we'll talk about forests. I don't know if I have any of that. I mean, that kind of says it all right there about energy use. And then I think here, I'll make the point that I've made in other places. There is a lot of talk now about how renewables for electricity production, this is talking about all of energy, but for electricity production, wind and solar are going to surpass coal either very soon or next couple of years. And that's good. That's a good thing. But it makes you think that coal use is going down. And I think coal use actually is going down. I'm a little confused with some of this because one of the charts showed it was going down. But fossil fuel use is not going down. And while it will go down as a percentage of energy, because renewables are going up, let's just say we're releasing 1 trillion units of fossil fuel energy with zero renewables. If all of a sudden we were, and that's 100% of our energy. If we figured out how to make renewables be 2 trillion units of energy, then and fossil fuels didn't change, then fossil fuels all of a sudden would be 33% of our energy mix because renewables would be 2/3. But that doesn't matter because the amount of fossil fuels is the same. It hasn't gone down. It's releasing CO2 into the atmosphere at the rate it is. And it doesn't, again, the Earth doesn't care what percentage of fossil fuels we use. It only cares about the emissions. And that's a big issue that I think people have to really be careful about. And you're going to see a lot of discussion about the percentage of renewables. But the problem is that doesn't stop climate change. What stops climate change is getting rid of fossil fuels. And people think go ahead.
I mean, even that isn't completely true, in that it's what's the excess carbon in the atmosphere is what determines how much excess heat gets trapped. And we can stop emitting every last carbon atom tomorrow. That doesn't mean that the kinds of disruptions that we've been seeing over the last year and a half will suddenly stop.
Right. By stop, in that case, I meant stop making it worse. And by the way, it might get worse on its own after a certain point with tipping points and things like that and feedback loops. But what I meant by stop is humans stop making the climate worse. And we can do that only by stopping our fossil fuel emissions and a couple other geoengineering things, which we will probably talk about a little bit later. But yes, thanks for the clarification, Eli. Forests. So now we're going to talk about forests in this article. And by the way, we're talking about the 2023 State of the Climate Report, a new paper that came out last Tuesday. It's subtitled Entering Uncharted Territory. Forest. Between 2021 and 2022, the global tree cover loss declined 9.7% to 22.8 million hectares per year. Similarly, the Brazilian Amazon forest loss rate decreased by 11.3% to 1.16 million hectares per year. And further reductions are likely to occur as a result of the election of a new president of Brazil and several recent legal decrees. However, humanity is not on track to end and reverse deforestation by 2030, despite pledges by more than 100 world leaders in 2021 at COP26. Moreover, forests are increasingly threatened by powerful climate feedbacks involving processes such as insect damage, dieback, and wildfire. For example, the historical record-setting wildfires in Canada, which burned 16.6 million hectares this year as of 13 September, were partly related to climate change. This resulted in emissions of more than a gigaton of carbon dioxide, which is substantial given that Canada's total greenhouse gas emissions in 2021 were roughly 0.67 gigatons of carbon dioxide equivalent. How quickly such emissions can be reabsorbed by post-fire recovery is uncertain, and there is a real risk that increasing fire severity will cause unrecoverable carbon loss in a warming future. And I'll also add that the room we did last week was on how vapor pressure deficit, which we won't really get into again, but that the Earth, which was getting greener because more CO2 does help plants grow. That's one of the factors, but there are many other factors that either help or hurt plant growth. Obviously, high temperatures hurt it. A drought hurts plant growth. But the other is one I didn't even know much about before, was vapor pressure deficit, kind of related to the relative humidity. As the world warms, the amount of water vapor that the atmosphere could hold increases by 7% per degree. But then if the world doesn't actually have all of that moisture in the air, then there's a difference between what it could hold and what it is holding, and that's called the vapor pressure deficit. And if that increases, that hurts plant growth, as we learned about last week. So we'll not get into that again, but you can listen. That is, if you go to the Climate Chat YouTube homepage, that live streamed room from last week is now posted there. And that's what we're going to hopefully do from now on, our past rooms on YouTube. Okay. Now we're going to talk about oceans and ice. By the way, this is not, there's a lot of stuff here, but it's relatively short and clearly written, and it's very high level. So it's not, I think it's hopefully quite understandable. I would normally summarize a scientific paper, but this paper is already summarizing what it's trying to say. And it's also written in plain language so that it's easy to understand. So hopefully, but if you have questions, you don't understand something, please raise your hand and we can talk about it. So oceans and ice. Ocean acidity, glacier thickness, and Greenland ice mass all fell to record lows, whereas sea level rise and ocean heat content rose to record highs. The increase in heat content and the rapid rise in sea surface temperature are especially troubling because they could have many serious impacts, including the loss of sea life, coral reefs dying because of bleaching, and a rise in the intensity of large tropical storms, like we just saw, by the way, in Acapulco, which was incredible. I don't know, hasn't gotten much coverage, but there was a tropical storm that increased to a Category 5 hurricane in about 12 hours, and that was never seen before.
If
it was absolutely
if I weren't
devastating.
on Twitter, I wouldn't know that it existed. And even still, it's not news that's getting reported. It's, just people's feed and people that I follow reposting it. I mean, it's really astounding.
Yeah, like Acapulco is a modern resort city, had many condominiums, modern buildings along the coast for miles and miles and miles. And essentially every single window got blown out on every building facing the coast. And serious devastation. I just saw something this morning because you didn't see what happened inland, but inland devastation is really quite serious too. And, and Acapulco is a modern city built with modern, construction techniques. These were nice looking buildings like Miami, and just shows you what a Category 5 hurricane can do. I think this was the first Category 5 hurricane ever to hit that coast ever.
Yes, the coast of Mexico, the Pacific coast of Mexico. And that was one of the haunting things. It's like, here you go. Here's a trailer of what's heading your way, Miami. I know that they have had more furious storms on the Atlantic coast. And in fact, there is a building standard, which is Miami-Dade. So when it's known throughout the architectural products industry as the Miami-Dade standard, because they're the place that has the most wind-driven rain. Well, at least that in the US, and it became de facto industry standard. But yeah, it's coming.
It's coming.
Well, they'll be ready.
It's here. There are also growing concerns that the Atlantic meridional overturning circulation of the AMOC could pass a tipping point and start to collapse this century, possibly between 2025 and 2095, which would significantly alter global precipitation and temperature patterns with potentially major harmful consequences for ecosystem and society, including reduced natural carbon sinks. Yep. We have to look at that Armstrong-McKay paper there. Climate impacts and extreme weather. Climate change is contributing significantly. I should say, by the way, we've talked about AMOC collapse a lot here. So anyone who's listened in on Climate Chat already knows a lot about AMOC collapse. But let's just say I call it the mother of all tipping points. And it could happen in 20 to 30 years. And we're not doing anything to protect against it. So, and everything, all the stuff we are doing, trying to reduce emissions, that won't stop it. There's only sunlight reflection methods can stop it. Anyway, climate impacts and extreme weather. Climate change is contributing significantly to human suffering. Climate-related impacts in 2022 include another billion-dollar flood in the United States, which occurred in Kentucky and Missouri between 26 and 28 July, and the third highest frequency of extremely hot days. Between 2021 and 2022, the area burned by wildfires globally decreased 28%, but wildfire activity in the United States rose by 6.3%, from 2.88 million hectares to over 3.07 million hectares over the same period. Many climate impacts are expected to further intensify in the coming years, and we may have already experienced an abrupt increase in certain types of extreme weather, possibly surpassing the rate of temperature rise. And then, by the way, they have some pictures here, which I guess I can describe. There's people like going through the remnants of their home, maybe a tornado or something, someone carrying somebody out of a flooded house. I don't even know if it's like fire, smoke surrounding whatever that is. I don't even know that. And this is a really strange one. A woman sitting in a chair in her house, smoking a cigarette, but the water is up to above her stomach, and she's just sitting there like she's just hanging out. Very strange. And then people moving their belongings through flooded streets, and then this is hurricane damage somewhere. Looks like, Florida, but I don't know. No, it actually tells you. That's the Philippines. Okay. In 2023, climate change likely contributed to a number of major extreme weather events and disasters. Several of these events demonstrate how climate extremes are threatening wider areas that have not typically been prone to such extremes. For example, severe flooding in northern China around Beijing killed at least 33 people. Other recent disasters include deadly flash floods and landslides in northern India, record-breaking heat waves in the United States, and an exceptionally intense Mediterranean storm that killed thousands of people, primarily in Libya. As these impacts continue to accelerate, more funding to compensate for climate-related loss and damage in developing countries is urgently needed. The United Nations New Loss and Damage Global Fund, established at COP27, is a promising development, but its success will require robust support by wealthy countries. And here they, after this, they give a list of recent climate-related disasters since November 2022. I'm not going to, record-breaking heat waves in Argentina and Paraguay, heavy rainfall in atmospheric rivers in the western United States, Cyclone Gabriel in New Zealand, record-breaking temperatures in Southeast Asia, China, and South Asia, intense wildfires in Canada, tropical cyclone Mocha, Miramar, tropical storm Mawar in Guam, deadly heat in southwest, southern, and midwestern United States. 6 people died in southwest Japan because of extremely heavy rainfall that caused floods and landslides. Okay, that's enough of that, but there's a bunch more. So now we're getting near the end here where they're now making recommendations. Scientists warning recommendations. Motivated by recent events. Oh, we have Mark. You have a question mark. That's a question mark is probably a funny thing. Mark,
good one.
Yeah,
good
go
one.
ahead.
Question
probably
mark.
the first time you heard that. Anyway, no, go ahead.
Remarkable. So one of the interesting things, you mentioned the Libya flooding, and most of those fatalities were linked to the failure of 2 large Libyan flood control dams, of all things.
Correct.
And they had not been properly maintained. And so one of the interesting things to be tracking over the next decade will be the number of dam failures induced by climate change, where the original spillway design has been superseded by new precipitation totals.
Right. And we had something like that happen in California that was very scary. What was the name of the
Orville, exactly right.
Yeah, Orville, yeah.
Spillway undermined and started breaking apart, and they had to evacuate 250,000 residents downstream of the dam, not too far from Sacramento.
That's right. And regarding that in California, everyone's, Libya, they probably didn't maintain their dams very well. They kind of deserve it or something like that. Well, in California and all of Central California, there are all these berms and dams and things that were built by farmers like 100 years ago that are keeping areas dry today. And they're not engineered, they're not maintained by the state or anything like that. They're just on people's land. And so an earthquake or atmospheric river flood or a dam spill or something are going to just knock these things down. And so California is sort of like Libya in that sense. It has all these sort of not maintained water control things that are happening. And this is true. And by the way, I think the more general point that you're making, and this is certainly true, is that our world was built, the human constructed world was built for a climate that no longer exists. So things like storm drains were built for amount of water that we now have that totally surpasses that by multiple fold. And that's why we saw New York flooding just a month ago in Brooklyn and things. And on and on. And where our waste disposal, our water treatment plants are located. Once the sea level rises, it's going to flood those places. Yeah, go ahead, Mark.
Yeah, I was going to say the really good example has the recent series of two major hurricanes in the late teens in South Carolina took out more than 50 dams. And I forget if there were high fatality counts. I don't recall. I think there were more deaths in that Hurricane Matthew, and I want to say Florence might have been the other one. But we saw a huge radical shift in South Carolina's posturing, and they've gone out and evaluated the inundation zones for every single dam in their state now. And we're in the process of doing the same in Virginia, because there's just so many of these farm-built dams that were thrown up with a bulldozer. Right. We used to call sugar levees when I was in the I did a year with the Corps of Engineers, and these loosely compacted barriers, they're not really even dams. By the way we define them from the construction process, they're just bulldozed and backhoed into place. And if you're lucky, they ran the cat over it a few times to compact it, but they're not designed with any kind of drainage systems or adequate spillway structures. It's just a real crapshoot. And on top of that, state governments issue agricultural exemptions to farmers.
Mm-hmm. I saw an amazing thing, I think it was a year or two ago, when one of these levees in California broke, and there was like water spilling through it, and the farmer loaded up a pickup truck with rocks, and he drove the pickup truck quickly and jumped out. So it sort of drove on the top of the berm where it was still good, and then it flew into the crevice where it had broken to sort of cause a dam. And I think he did that with two pickup trucks filled with rocks. He drove them into the hole to try to, which I think worked, actually. I think he did a good job of slowing it down enough that they could start putting dirt on top of it and everything. So anyway, you can see that maybe on YouTube or something. All right, let's get back. We have ENS. I don't know how you say that. ENS, do you have a question or comment? And
yes,
you can lower your hand.
This room. Thank you. Am I audible? Yeah.
Yes, you are.
I hope. Yeah. Sorry for my English. Yeah, I'm a German native language speaker, and so yes, of course, climate is changing. Climate always has changed, and so my question is: as living in the northern part of Germany, Hamburg, the port city, we have seen back in the 1970s severe damages to our city. City centers got flooded, and I really admire our western neighbors, the Netherlands, our Dutch neighbors. And this is my point. So there's one way. We can think about how to reduce things, the impact, but also how to protect ourselves. And you were talking about dams. And please be assured, that especially our Western neighbors, the Dutch people are doing a very, very good job, but also us in northern Germany, Lower Saxony, and also Hamburg is doing a great job, Bremen, not to forget. So won't you think that it would make sense to have a two things in parallel in the planning. So, of course, reducing pollution. Of course, we want to save the earth, but we also want to protect our human beings here, wherever it is they are wherever they are becoming endangered by climate change. What's your take on this?
Yeah, so there's three things. We get to choose the amounts of each. One is called mitigation, how much we stop emissions, how much we try to stop the climate from changing. The second is adaptation. That's what you're talking about, like building higher dams or stronger dams and doing cooling areas and whatever. That's adaptation. And the third one is suffering. So depending on how much we do of the other two, that's how much suffering we're going to have. And we're going to have a lot of suffering because right now we're doing almost no mitigation. We're kind of doing reactive adaptation, but you really can't adapt to many of these things. You talk about the dams that are working in Germany, but there's also been over the last 2 years or so been several videos of floods going down the streets of German cities with cars floating by, and that's because the storm drainage is not even close to enough for the record rains. It's really hard to emphasize that so the average rain hasn't changed very much, but extreme rainfall has. And when you get 10 inches of rain, 20 inches, 20 inches of rain is insane. 2 inches of rain is a lot, right? 10 inches of rain is biblical. And there's no storm drains that can adapt that. And so the problem is that you can do the adaptation you can do, but there's a lot of adaptation you can't do. For example, if you have a very long-term drought, it's really, really hard to, provide food. Or if you have a flood, which also damages crops. And then, of course, if you live in northern Germany, you have an AMOC collapse that we talked about here on this show many times. Your whole world is going to turn upside down. That you're going to drop. So far, Germany has probably warmed, 2 Celsius on land, maybe 3. And now you're going to drop 5 or 6. And because all of that warm water that's been keeping Northern Europe, keeping it a nice place to live, is going to stop in 20 or 30 years. And it's going to turn everything upside down. The one study I could find on a particular country showed that the arable land, or the places where you could grow food in the UK, would drop by 2/3. Probably something similar for Germany. Germany, not as bad because you're not as far north. Farther north you are, the worse it gets. But you're in northern Germany, so that's going to be pretty bad. So yes, we do have to adapt where we can. But we're talking about, what this paper is trying to say, is that the changes are so monumental compared to human society that adaptation, you'll be able to adapt to some things, but not really to a lot of these things. So in other words, because we're doing so little mitigation, there's going to be a lot of suffering. Yes, we should adapt and we're going to need to adapt. But for example, Florida, the bottom third of Florida probably won't be on the map sometime next century. And you say, well, we'll build a seawall. Well, you can't build seawalls in Florida because the rock is porous. So if you just built a wall, holding back the sea, the water would simply go under the wall because, and that's how they have floods today. They have floods, like daytime floods, because the sea level is already pretty high. And then the roads just start flooding. It's not water coming from the ocean into land. It just comes out of the ground and comes up because, again, Florida is built on porous limestone. So anyway, so yes, we'll try to adapt, but don't take a lot of comfort in that adaptation, I guess is what I'm saying. In other words, we better really work on the mitigation part of it as much as we can. So we're going to
do you allow me one question?
Yeah, please.
Is it proven that the mitigation would work instead of us not spending money on adoption?
Well, no, it's not one or the other. You have to do both. I'm not sure what you're saying. You should. Should we send it? Should we spend it on mitigation?
Yeah. Because nowadays, everything is spent into mitigation. But I do see, besides of northern Germany, and as said, our beloved neighbors in the Netherlands, there is few adoption initiatives, but more mitigation initiatives where I do not see a proven impact of that this will help, because the globe is warming. Yeah.
Well, the globe is warming because we're not really mitigating, by the way. I remember, I'll just say it very simply, as this paper talks about. Fossil fuel emissions are at a record high. I'll say it again. Fossil fuel emissions are at a record high. So you're saying that we're mitigating. No, we're doing. It's not as bad as it could have been, right? If we didn't do the mitigation that we've done, fossil fuel emissions might even be higher, but that's not really an excuse, if you know what I mean. Our job and our requirement is to get our fossil fuel emissions to as close to zero as possible. And let's turn off that person who's writing on the screen with a V. Hey, we got Leon here. Wait a second. Leon, welcome.
I've messaged you every which way, but
okay, sorry. Hey, Leon, welcome. Who's ever doing the writing there with a V in the name, can you kick him out of the room? I don't know how to do that here.
Allow me one question. We are seeing, especially in Germany, a lot of mitigation initiatives, and that is strangulating our economy. Yes, and also private people are paying the highest energy prices. Yeah, we have seen that, but still, to my knowledge, there is not a reduction in sourcing oil and gas out of the Mother Earth. Yeah, it is not declining so far. So
correct.
What's your recipe? How to make an impact on that?
It's very simple, by the way. It's so simple, yet no one will even talk about doing it practically. You have to phase out fossil fuels. Governments have to say that starting in 2030, we won't sell any more fossil fuel cars. Starting in 2035, we won't allow any more fossil-based electricity. Starting in 2040, we won't allow any fossil energy. And also, starting right now, immediately, we will stop all new fossil fuel infrastructure. No new, coal plants or coal mines or oil fields. Stop all new things. The International Energy Agency said it's not possible to meet climate targets unless we stop all new fossil fuel infrastructure starting immediately. So that's an easy one. Stop all subsidies, or I should say phase them out. A lot of these subsidies are meant to sort of help the public, so you have to phase them out. So these are really, as it's called the first law of holes, HOLES. The first law of holes states, when you find yourself in a hole, stop digging. And we are in a hole. So it's caused by the burning of fossil fuels. So what's the obvious solution? Stop doing it. The good news is that if we stop doing it, we will actually save trillions of dollars, because renewable energy is cheaper than fossil fuels. And that's right now just based on current prices. But when you take climate impacts into account, it's incredibly less expensive than fossil fuels. So what we're doing is we're taking the most expensive, most damaging form of energy, and we promote it by subsidizing it and by other rules and regulations and by inertia and all that kind of stuff. So we could, if we wanted to, we could actually take steps to phase it out. So anyway, let's quickly go to Adam, and then to see if Leon can join us. Go ahead.
Good morning.
Good morning.
So I had one question, but you just sparked another one. I'm not a scientist at all.
Okay.
I'm completely. So just trying to understand the situation. And from what I've been hearing and reading is if we were to stop fossil fuels and rely solely on renewables, then that would actually speed up the rate of warming, given that the aerosols would go down, which are helping reflect heat back out of the atmosphere, the Earth's atmosphere.
That's correct.
I'm probably wording this wrong. So that's one thing that I would love for you to clarify on, if you could. And then the second thing is, you mentioned earlier about the Earth's energy imbalance and how that's rocketed since only 11 years ago when you shared a platform with James Hansen and talked about it then. And doesn't physics therefore mean that it's unavoidable that temperature rise is going to increase dramatically no matter what happens? And by dramatically, I mean catastrophically, even meaning our extinction as a human species.
Okay, let's talk about that. And we have Leon Simons here, by the way, as co-author with James Hansen on that paper that's coming out next week, by the way. So we'll definitely talk about it the following week. It's coming out next week. This is on global warming in the pipeline, which is really what you're talking about. So this is an important thing. So let's talk about, I'm going to give you sort of the high level idealized situation. If we cut our emissions to zero tomorrow, what would happen? By the way, to be clear, we're not cutting our emissions to zero tomorrow, but, and this, what I'm telling you won't really count if we pass tipping points and sort of runaway feedback loops that take it out of our hands. But let's talk about the situation while it's still in our hands. If we cut our emissions to zero tomorrow by using 100% renewables, let's say, yes, the aerosols that are currently cooling the Earth by 0.5 to 1 degree would go away and the temperatures would immediately go up. However, we would also stop putting methane in the air. And methane is an extremely powerful greenhouse gas that causes about 2/3 the warming of CO2, even though, and listen to this because it's kind of crazy, the amount of extra CO2 we put in the air is 120 parts per million so far. The amount of methane we have put in the air is about 1.2 parts per million. 120 for CO2, 1.2 for methane. And methane has about 2/3 the warming of CO2. The bad thing about CO2 is it lasts essentially forever in the atmosphere, hundreds to thousands of years. But methane only lasts like a half-life of 12 years. So when you cut all emissions, the cooling aerosols go down, but the warming methane goes down. And the two of them roughly cancel out. Okay? That's one thing. The other thing is... Go ahead, Eli.
You did slightly misspeak. The methane is 100 times more potent the year that it's emitted, and about 25 times as potent averaged over a century.
Well, they're about 30 times over a century. But I'm not talking about a century. I'm talking about the actual warming in the atmosphere right now. If we stopped all methane emissions, we would drop by like 1 part per million. At the end of 20 years, very little methane, man-made methane, would be left. And that would cool the Earth. And it would cool the Earth by about the same amount as the aerosols would warm the Earth. Lack of aerosols would warm the Earth. Those are two things that cancel. The other two things that cancel is that there is warming in the pipeline, as you just talked about. And again, not taking it, I'd love to get Leon's take on this, because this paper that's coming out next week that Leon's a co-author and talks about the very long-term feedbacks of warming, not the ones we normally talk about sort of this century, but if we talk about the shorter ones this century, there is warming in the pipeline, and that would continue to warm the Earth, and that's something that would make it warmer. However, if we stopped emitting CO2, the oceans, as you might know, take up, roughly speaking, 1/3 of the CO2 we put out every year. But if we stop putting out CO2, it would still continue to take up CO2 at the same rate for quite a while until finally it equalizes. But so that would lower CO2 levels in the atmosphere, and that would cool the Earth. And those two things roughly cancel. and I'm going to emphasize the roughly part, because there's a number of factors in there. As Hansen and Leon Simons and others have shown that, maybe the aerosol cooling is actually more than we think. So dropping that would mean more warming than we think. and other factors, and also the long-term feedbacks of Greenland continuing to melt, and then when you don't have white ice reflecting it, you have dark land absorbing heat. That's very long-term, but still, that's when you really start to get very high temperatures. And so those kind of things could continue to happen. But then the quick answer to all of this is, in addition to cutting our emissions to zero, since first of all, we're not even doing that, we need to take CO2 out of the atmosphere artificially. And that would, again, cool the Earth and get it back to a safe level. Take a long time, cost a lot of money, but can be done. And then the other thing we do is we artificially cool the Earth temporarily while we reduce our emissions and take CO2 out of the air. That's called sunlight reflection method, sometimes called solar radiation management, sometimes called solar geoengineering. And we can do that too. And we're going to have to do that because we're not doing anything else. Things are going to get totally out of hand. And we're putting ourselves in a position where we're going to have to do that. Before I go to the other questions, Leon, do you want to jump in on the conversation here and give a comment on what we just said? Welcome. Great to have you here.
Hi. Thanks. Do you hear me?
Yes, we do.
Okay, great. Yeah, sure. So just let me think about what you just said, because
okay.
Of course, that's the big if, and that's, I think, the discussion which we'll be having a lot in the coming weeks as our paper will be published next week. Is indeed the warming in the pipeline and what we, of course, if you talk about warming in the pipeline, and you always have to take an assumption, a scenario, and the scenario we use in our paper is a stabilized greenhouse gas forcing, which you mentioned is at the of greenhouse gases, right? You mentioned methane, you mentioned CO2, and of course that's in a way that's purely hypothetical, because the greenhouse gas concentrations in the atmosphere are not stabilizing, let alone for 1,000 years. So in practice, the greenhouse gas forcing is increasing. And you mentioned the net zero scenario where, like, magically all the greenhouse gas emissions and aerosol emissions go to zero. That's even less likely, of course, because I wrote I think on Twitter what that would mean.
Yeah.
That would mean I think 1.24 billion cars stop driving, stop heating houses, stop producing food, stop 100,000 flights a day. What's happening now? So that, I think it's important when you hear this. To me, at least when I hear this net zero scenario, I just try to understand first what it means and what it would take, and I translated it in one sentence as the instant human extinction scenario, because that's
right.
That's the only way that's possible. In especially what is often shown is a scenario where these emissions go to zero in 2020.
Well,
and of course,
I think anyone who says it in 2020 is only talking about a academic exercise, not a serious suggestion, I think, right?
Yeah, but it is shown that
but even 2050, as you're saying, is a very optimistic scenario without carbon capture.
What you say is that it's only academic, but it's not only academic. When Al Gore gave his last TED talk, that's what he showed at the end as a hopeful message, that if we stop emitting greenhouse gas today, warming will stop. And then he shows a graph where emissions stopped in 2020, and then that's of course it's purely hypothetical, and I don't think it's right to provide that as a message of hope. I think that's completely wrong. It's at least for me, I don't take hope out of that, because I understand. That's what I said. For me, that means the scenario means that the instant human extinction scenario, which is not hopeful in my opinion.
Right. By the way, I want to emphasize something you said, because I think it's the number one thing that people are confused about the global warming and the pipeline paper that is, again, has already been published as a draft. And now what's going to happen next week is the publishing of the official peer-reviewed version. And again, this is like by James Hansen, and Leon here is one of the co-authors. And Leon is an expert on the warming of the oceans due to changes in shipping and aerosols and all the things, many of the things that we were talking about. And Leon is a co-author of the paper we're discussing today as well. But the key point that Leon just said, and I'm going to say it again, because this is, I think, the number one thing of confusion, is people see the title global warming in the pipeline, and in their head, that means to them that this is unstoppable. It's out of our control. This is the warming that's going to happen no matter what. And what Leon is saying is, no, this is a scenario. Just like in 1896, Svante Arrhenius did a paper, the first paper on global warming, that said, what would happen if CO2 levels doubled in the atmosphere? How much would the world warm? He wasn't saying that CO2 levels were going to double. He didn't even think they would. I mean, or take thousands of years back then. He thought he'd be very surprised about how fast we're trying to make that happen. So far, we've increased them by 50%. But it was a scenario so that he could do a calculation. And what Leon is saying is that Hansen and he and others did a scenario saying, what if we held the forcing of greenhouse gases constant for a long time, and see what happens then? What other kind of feedbacks would kick in eventually to warm the Earth further? And they found that if you did that the world would warm by, well, we'll see next week what the peer-reviewed version, but the draft version said up to 10 Celsius of warming, which would be way beyond catastrophic extinction level event. But that would be in a very long time frame. But that still is a scenario. And whether we hold global warming forcings constant is up to us. Right now, we're not holding them constant. We're trying to increase them as fast as possible. In fact, in the draft paper, they said, I think by the end of the century, at the rate we're increasing the forcing, it would double by the end of the century and be on the level of previous mass extinctions levels if we continue increasing it. So it's not staying constant like the paper assumes, it's going up. But if we chose to, we could turn that around and decrease the forcing, and then we wouldn't have that warming. By in the pipeline, what they really mean is the very long-term warming under any scenario, really, right? I mean,
no, not only long term. We discussed the short-term warming, the medium-term, and the long-term.
Okay. Yeah, but many others talk about the short-term side of things too, right? What do you think of what I said about, in terms of short-term, that the warming, quote, warming in the pipeline, the energy imbalance, would be offset by continued uptake of CO2 by the oceans if we had human extinction tomorrow and we cut all our emissions to zero? Do you think that's roughly correct?
Yeah, so that's also a scenario, and in that scenario, you assume that the AMOC will not shut down, and so there's a lot of assumptions in there, right? And you always have to do make assumptions and describe those assumptions, so what an important aspect of that is these aerosol emissions over the oceans, and not just the oceans, of course, but what these aerosol emissions have been doing, and it's also in this paper we're talking about today, is reflecting sunlight back to space directly and through increasing cloud cover and making clouds whiter and more reflective. Mm-hmm. So that and by reflecting sunlight back to space, there was less heat being absorbed by the land and the oceans, and temperatures increase less than they would have increased without these aerosols, without these sulfur particles. Mm-hmm. And has mainly been done on the northern hemisphere. And correct for that need, and that increases the energy imbalance, not from the space and the Earth, or the sun and the Earth, but from the hemispheres, from the southern hemisphere and the northern hemisphere, because there's less. The northern hemisphere is absorbing less sunlight. That's corrected by more heat flowing from the south to the north, not just through the atmosphere, or not just both through the atmosphere and through the ocean, especially the Atlantic Ocean. And the Atlantic Ocean, that's what we call the AMOC, Atlantic Meridional Overturning Circulation. Meridional means from south to north. So that's heat flowing from south to north. And now, when we reduce these aerosols, as we have we reduce the sulfur emissions over the oceans by 80%, including over the North Atlantic, then by reducing these emissions, less sunlight is being reflected back to space, and more sunlight is being absorbed, especially at like most months, and then certain months like June and July. For the North Atlantic, it matters how much Sahara dust is blowing over the North Atlantic, as we talked about a bit, or you talked about a bit. And now this year we had less Sahara dust blowing over the North Atlantic, which means that the effect that also increases the amount of sunlight that's absorbed by the North Atlantic, but also it makes the effect of the sulfur particle reduction in these months more pronounced.
Mm-hmm.
Because they don't have to compete with this air and dust, which is there normally the other years. So, and then going back to the AMOC, so many studies show that the global warming slows down the AMOC, but these aerosols increased the flow of the AMOC. And by reducing them, we can expect that the AMOC will slow down even faster.
I'm sorry, let's say this again. By reducing essentially the solar radiation management that we've been doing accidentally over the ocean, by reducing ship smoke, that will accelerate the collapse of the AMOC?
Yes.
Would you say that alternatively, if we put purposeful sunlight reflection methods, we did it on purpose, not by accident, and we purposely tried to cool the poles, especially, that could slow down and maybe even prevent the collapse of the AMOC?
Yeah, in theory, but so there's very little research on that. So I guess of course, in theory, we could increase. We could do anything in theory, right? But
Leon, is that a localized thing? So, for instance, you would, like, if you halted, let's say we wound the clock back and didn't have that in place, changing out the fuels, which we know we need to do. It's dirty, horrible, bad for life, period. If we had just changed the fuel in the Pacific, but not changed the fuel in the Atlantic, would that, is it a global thing, or is it an Atlantic thing, the way the aerosols affect the upwelling and stir?
Yeah, it's globally these particles have impact, but there's a study showing that if you increase they quadruple the amount of sulfur emissions, then they show that there is a strong increase in energy flowing from the south to the north. But we did the opposite, so we can expect a decrease. But then, if you really want to understand what's happening, so we don't know. Like the honest answer is we don't know, and we're just running the experiment right now, right?
We're gonna find out.
One way
or the other, we're gonna find out. It's probably not going to be good, whatever it is. Yeah.
So we have there's the models. There's such a big uncertainty in the models. There's some models showing that there's no effect of changing these, or virtually no effect of changing these sulfur emissions. And some say there's very large effect equal to about 10 years of greenhouse gas emissions. And that's the range of the models, which shows in a way that you cannot really trust the models because they are all over the place. So we need to learn as much as possible from this inadvertent aerosol experiment, as we call it in the paper. Right. But yeah, I just wanted to highlight that.
Sure.
If even in talking about this hypothetical scenario of the oceans absorbing heat and CO2 emission and the excess CO2, it's all it's very much dependent on the state of the oceans, and we are really changing the state of the oceans. So we are learning what this means.
I'd like to emphasize for everybody that, people talk about eventually over time, the natural systems will take up excess CO2, which is true over very, very long time periods. But one of the ways, as you're mentioning, is by the ocean sink. But as you just mentioned, that's a little bit questionable if the AMOC shuts down. But even if it doesn't, and we still have that ocean sink, it's still a catastrophe because taking up that much carbon dioxide will further contribute to ocean acidification, which is already having impacts on sea life. It's just beginning to, but we've seen it in terms of various crab fisheries seriously underperforming because they can't make their shells. And take away everything else about climate disruption, what we're doing to the ocean, through ocean acidification and other forms of pollution is a complete ecological catastrophe in and of itself. And it will come back to have effects on humans, considering how many humans are essentially fed by the ocean. Okay. So that's one point. The other thing, earlier on, there was a quick reference to a mega extinction event being driven in the future, and that's true. But we're already in a mega extinction event. Presently, that's mostly driven by things like land use change, whether that's plowing natural ecosystems under in order to build cities and shopping malls or what have you, or things like logging and mining. And this is among the fastest rates of extinction in the geological record. And the things that are unfolding with climate are only going to accelerate that further. And it doesn't get nearly enough attention because we're not doing enough about the things that are getting enough attention.
Yeah, good. Thank you, Eli. And Leon, if you want, you can turn your video on, because this is no longer just Clubhouse. We're doing Zoom and we're doing YouTube Live, and they do have video. So you're welcome to turn on your video if you'd like to. You don't have to. We have questions from, I'm going to try to say it, Verana Sanin. I hope I was close to that. Please, what's your question or comment? And you have to unmute. You're still muted.
There you go.
Still muted. One more time. Try it if you want it. Okay, go ahead. Nope.
Yeah. Great session, sir. My question is, I saw the article that due to the after the pre-industrial era, 600 gigaton of carbon is emitted by our activity. So it is mostly absorbed by oceans, like 240 gigaton. So in that 240 gigaton only causing the ocean acidification. So if you want to get rid of that acidification, what are the methods right now the people are trying? Because we are working with CCUS, carbon capturing and usage and storing technologies. So we are we have the technology to absorb the direct carbon capturing methods, but without deacidification of ocean, it is very tough to make a better place. So I need some guidance on that. At the same time, pre-industrial era have the ppm of 280, but now it is 418 ppm. So when I'll come with the calculations, it's showing that for every degree of increasing temperature, ppm, it will come around 6 gigaton of carbon emission. So I need to have some details from on that. Thank you.
So I'll repeat your question here just so people can hear it clearly. I think you're asking, the ocean's getting acidic because it's absorbing roughly a third of our emissions. The land and soils emit 20%-ish. And so roughly speaking, 55% of our emissions are absorbed by the Earth, and the remaining part stays in the atmosphere for hundreds of thousands of years. But as the ocean gets acidic, that hurts the building of shells and life in the ocean. And that's true. And what can we do about it? That was the first question. And that the answer is, well, first of all, if we take CO2 out of the air or out of the ocean, by the way, there's different ways to do that too. But if we take it out of the air, then it will reverse the process and CO2 will come out of the ocean and become less acidic. But we have to do this on a really big scale, we're not doing it today really at any scale. But if we did it at 40, 50 gigatons a year, and we reduce our emissions to as close to zero as possible, and we can't get to zero, but let's just say we got it down to 10 gigatons from 40 today, and we did 50 gigatons of carbon capture, which we've talked about here before. Very hard, but possible. About the size of the automobile industry. And if we did that, 10 would go to cancel the 10 we couldn't get rid of, but then we'd have minus 40. And then we would be reducing CO2 at the same rate we're currently increasing it. And that would bring down ocean acidity at the same level it's currently increasing. And that would still take a long time, take many, 50 years, 60 years. But we could do it. And since the Earth is too warm already, and we reach tipping points like AMOC collapse, we also need to cool the Earth artificially while we wait to do those other things. Now, the thing about, I didn't quite get to your second question about, we're putting up lots of emissions. We have to cut them as much as we can. Good news is renewables are cheaper than fossil fuels, so we can replace that. And we can also build carbon capture to reduce it. So, yeah, so we've talked a lot about that. I don't want to talk about that too much here today because we're trying to focus on these two papers, well, actually on this paper that Leon wrote, and it talks about this, but it's one of many big issues. So we'll get
emphasize. It is true, as you said, if we take out as much as we've emitted, then things will be restored. But the caveat there is that's if we don't go over any tipping points that lead natural systems to themselves,
right,
start emitting significant tons of carbon dioxide and methane. We're still, and there's a real danger of that from multiple different sources. And,
that's right. That's why these are all still scenarios.
they're scenarios, but we don't have accurate probabilities to and even measurements of the distributions of things to let us know with confidence that, well, we can be certain that that's not a risk, which is why more than anything else the sunlight reflection methods, SRM, are really important to reduce the risks that we are facing of getting into a scenario where the natural systems responding to what we've done wind up emitting more than we've emitted, because then it becomes a much bigger, harder problem, and it's a bleak scenario that we don't want to find out the hard way about.
Yeah. Let's move to Dr. Brian here. You have your hand raised. Welcome. And what's your question or comment? We didn't even get to the end of the paper yet, by the way, with the recommendations. I'm going to try to get back to that, but let's just handle these couple of questions here, and then we'll go on. Yeah.
Yeah, earlier today it was mentioned that, gee, if we go fossil fuels to zero, then the methane's going to come down really fast. But the stable isotope studies indicate that the superlinear increase in methane that we're seeing over the past couple decades is largely, if not mostly, from biogenic origin and not fossil origin. And that means that cutting fossil fuels to zero doesn't stop the increase in methane because of this biogenic origin.
Yeah, but if it's cows, we can cut the cows. And we are working on ways to cut it even with existing cows. A company called Ruminate, which has a feed that stops cows from producing methane. So, and also on top of that, I did, and I don't know if we did interview Robert Howarth, who's a Cornell professor on methane. Well, one of the leaders in the field, and we interviewed him a year or two ago, a couple of years ago now, I guess. It's also available. That interview is available on our YouTube homepage. I watched him give a detailed talk on this subject where he said actually a lot of the methane is from fossil origin, that a lot of it is because of our increase in fracking in the United States. Now, this was a couple of years ago, and maybe it's shifting now. But he was saying when you really take a look at where that comes from, it's not cows, it's actually fracking. So I think it's an open question, is all I'm saying. I'm not saying that's right or it's not right.
Landfill.
Yeah, the other source worth mentioning is that the terrestrial permafrost and the submarine permafrost has been increasing. According to Sir David King, more than 1,000 methane pit craters have been observed in northern Siberia, and that doubling rate seems to be one doubling per year. That's right. Based on the historic over the past decade. So there are a number of biogenic sources, not all of which are under our control presently.
Yeah, and if you take a look at my climate talks I gave back in 2006, 7, and 8, some of them are online. You'll see, what do I talk about? I talk about methane. I show people poking a hole in a lake and lighting it on fire, and it was just a crazy thing to see. And saying that the thing I worry about the most is exactly what you're talking about. Eventually, the Earth will start putting out more greenhouse gases than we do in response to what we have done. By warming the Earth, you melt permafrost. Permafrost holds twice as much CO2 as the entire atmosphere holds. And depending on the conditions, it might not release that CO2 as CO2. It might release it as methane, and methane's 100 times more powerful as a greenhouse gas when it's in the atmosphere.
And also, it's easier to get carbon dioxide out of the atmosphere via direct air capture than it is to get methane out.
Yes, although my brother was just visiting here as a company that eradicates methane. You don't have to capture methane; you just need to destroy it because it is so powerful. When you destroy it, it turns into CO2, but it has 1/100th of warming, so you don't care so much about that. But yes, but you're right, it is harder to do methane. And that's permafrost is only one of the places to get methane, as Dr. Brian was talking about. You can have the shallow Arctic Sea, where there is methane enclosed in ice crystals, and it's called clathrates. And if that starts to melt and releases its methane, it could easily be more warming than even if so far we're not reducing our emissions, but let's just say we decided we don't like this climate change thing anymore. We're going to go all out to reduce our emissions as fast as possible. But if the methane and CO2 release from natural sources, again, in response to the warming we caused, so call it natural or not, it's really a feedback loop. If that happens faster than we can lower it, then it's kind of game over, except for maybe solar radiation management, which we are going to do, by the way, because people will be very unhappy with climate change in the next decade or two. And the only thing that will change it rapidly, the only thing that fixes it is like CO2 reduction and CO2 removal. But that takes a long time. The only thing that makes a visible impact on the climate in the short run is sunlight reflection methods. Let's move on to Eric, so we can get all these questions out of the way here. And then
quick point though, not only is the AMOX slowing down, but heat transport into the Arctic is increasing, and that is via the Norwegian current. And it is likely that those two things are related, that the conveyor belt doesn't just stop turning, but some of it just goes in places where it hasn't been going. And that is what will particularly be threatening to mobilize methane that's trapped in subsurface sea ice above the gas hydrate stability zone.
Okay. That's a new one I haven't thought about before. So good. Hey, Eric, welcome to the stage here.
Thank you so much, Dan. Hey, Dr. Simons, is that how it's pronounced?
Yeah.
Hi. For those of us who may never get around to reading the actual paper, can you give us like a couple of minutes, like 2 minutes about the methodology? Are there multiple models that are averaged together? This is the high level 2 minutes on like how was the study done?
You're talking about the glow, because you remember he is co-author of the paper we're talking about today. But
that's what I mean. The one we're talking about today.
Oh, okay. Leon, can you talk a little bit about this 2023 report on the climate and how that paper was put together? If you're still there listening. Oh, your mic is off. Yeah, good.
Yeah. So it's not really a study focusing on climate models. It's more focusing on what we actually see happen. So that's I think you went through it already, but we really see the rapid changes happening in the around the planet. We see the I think maybe start with of course the greenhouse gas concentrations. So we see the greenhouse gas concentrations reaching record levels. In the meantime, we see sulfur, especially sulfur emissions, reaching very rapidly reducing. And I first mentioned these two because that's what's really driving climate change. Greenhouse gases cause warming, and aerosols, mainly from sulfur, reduce warming or limit the warming from greenhouse gases. And if we reduce these sulfur emissions, we increase a net forcing effect. And then the effect from that is an increase in the Earth's energy imbalance. So these two, the greenhouse gases and the aerosols, they cause a net forcing, which is calculated also in watts per square meter. And the Earth's energy imbalance is also measured in watts per square meter. And then we see now that the Earth's energy imbalance is reaching about for the past 3 years on average from the NASA satellite data, 1.4 watts per square meters. And that's lower, of course, than the greenhouse gas forcing of 4 watts per square meter, because that includes the warming we already see. And if the planet heats up, it will radiate more heat to space, and then the net warming that will reduce the energy imbalance. But then, so to make a long story short, so we see the Earth's energy imbalance increase faster and faster. It has more than doubled in the past 20 years, and now that causes more heat to accumulate in the system, especially in the oceans. And now with the La Nina, that has limited the warming a bit for 3 years. And now we have a El Nino starting, and how much of the heat that has accumulated in the oceans is coming out, and it's starting not just to heat the atmosphere and causing all these record temperatures, but it also causes the sea ice to reach record lows, and of course the ocean surface temperatures reaching record highs. And these are all happening at the same time, simultaneously. And we also show, of course, the forest fires in Canada emitting almost 2 billion tons of CO2. So these would be very crazy in a way, or scary, as we call it, by themselves, right? These very high anomalies, record high, shattering high, would be quite scary by themselves. But it's all happening at the same time, which makes it even more scary or even more shocking. And because heat normally flows around in the system, right, and also in the Earth system. So you would expect certain parts to reach record highs, but if it's all happening at the same time, that's even more an indication of something extraordinary happening. And Yeah, that's what we try to show in this paper. It's an update of a study in 2019 by William Ripple and Christopher Wolf et al., which was signed by 15,000 scientists around the world to declare a climate emergency. And now we really see this emergency taking shape more and more.
Very good.
Thank you so much.
On what was mentioned, Leon, do you happen to know of any estimates of how much the additional black carbon soot deposition due to the increase in wildfire is contribute to increased rates of sea ice loss?
No, I don't know. I don't know of a study looking at that specifically, but I think so. There's a number of things happening. So the sea ice loss we saw now, the biggest sea ice loss we see is around Antarctica this year. And no, like in the past 30 years, we saw a big decrease in Arctic sea ice, but this year we saw even more decrease around Antarctica, which was in the past month about 1 million square kilometers lower than the previous record low. And that's really a lot of sea ice missing, which also, of course, takes a lot of heat. And that's now the it's Antarctic winter, or it was Antarctic winter. So that means mainly that it didn't grow during the winter. But now the Antarctic summer is starting. And with all the sea ice missing, there will be much less ice. And much less ice means that there's instead of reflective white surface, there's a dark ocean, which will absorb much more heat from the sun when the sun started shining upon it. And so that's one important aspect. And then going back to your question about black carbon, so there's of course we can expect that if there's more soot depositing on the ice on Greenland and on the Arctic ice, that will increase or decrease. We call decrease the albedo, so decrease the reflectivity of the surface, and that will heat the surface. And another aspect, which is not talked about a lot, is that once the ice starts heating, and there's nutrients from the fires and from because these fires, it's not just soot, but it's organic compounds which have different chemical makeups. So depending on the trees and etc. And then, but that also feeds algae. And if these algae start growing on the ice, that also decreases the albedo and increases the heat absorbed. And that's also a strong feedback, which will increase the melting of the Greenland ice sheet further. So that's another.
And that feedback, those two feedback. Well, the black carbon soot is probably included in the IPCC models, but is the microalgae growth on ice is that anywhere accounted for?
No, not yet. But what I'm really even more like when we talk about rapid melting of ice sheets, because I think that's the important question here, right? How fast will the ice sheets melt? And I've been at a number of meetings, and sometimes there are scientists or people who say, okay, this will take thousands of years. It's really not relevant. But this doesn't. That's just going by the models, which don't take a lot of stuff into account. If you have these for example, these rivers, these atmospheric rivers, which is quite a phenomenon, which has been looked at only for not so long yet. And if you have these atmospheric rivers bringing rain instead of snow to Greenland, for example, and that will transport a lot of heat, and that will melt the snow much faster. Living in the Netherlands, we have of course we have ice, and we can go ice skating even if the temperature goes above zero. the ice will start melting a bit, and we can still ice skate for a while. But then if it starts raining, we no one ever goes on the ice anymore, because we know that the warm water will really rapidly melt the ice, and that's a way of rapidly transporting heat from one place to the next. It's through water, and so that's really something we have to take into account, and it's really not.
And so what I'd like to emphasize for everybody is we are seeing phenomena become more frequent, phenomena that are not well represented in the data that all of these climate models are validated against.
Yeah. Okay.
Yeah, because they're validated against the past, which we know and we understand a bit, we can use to build these models, but we cannot build them on the future, which we don't know about. And then of course there's a lot of scientists doing very hard work to understand all these causes, or these important forces at play. Like, I think it's called a study called Black and Bloom, which is really looking at that aspect of soot and algae blooms on the Greenland ice sheet.
Okay, let's Dr. Brian, do you have a quick question? I want to move back to the paper.
Yeah, here's a quick one, and that is humanity's turned off this marine sulfate aerosol signal over the past 1 to 4 years, let's say. And yet, just this summer we saw Florida temperatures of the ocean of 101 Fahrenheit. What is the natural impulse response timescale from turning on or turning off these marine aerosols to when the planet responds from a radiative balance standpoint? Do you have a sense for that timescale?
Yeah. I've get that question a lot, and it's like, if you look at the data, which we are looking at because I understand the question. It's a logical question, but that comes from from seeing all these shocks happening now. And then, so what we try to show in our data, or in our paper that's coming out, is that we see this already happening for years, and not just from these sulfur emission reductions from shipping, but also from China reducing its emissions by almost 80% since the Olympics. Because China has installed these desulfurization system, as they're called, to wash all the sulfur emissions from the smokestacks, and then that also caused warming. And then, so we see this really from the satellite data, with a reduction in sunlight reflecting back to space. This means more heat is absorbed, and then we see the oceans, especially in the northern hemisphere, mid latitudes, warming quite rapidly. And maybe you don't see it, but that's really, if you look at the data, we can clearly see that there's all this heat has been accumulating there already for the past 10-15 years, and then more strongly in the past 3.5 years, and now it's coming out. It's coming, and that's why I mentioned also the El Nino, and that now it's becoming more apparent for all to see. If you look at the data, we've been seeing it already, and now it's coming to the surface, and it's coming to, and it's causing it's contributing to all these extremes happening everywhere, not just of course also in the around Florida and around, and then of course it's also natural variability, right? It's sometimes, as I mentioned, sometimes heat flows to one place and sometimes to another. With the El Nino, the heat comes to the surface, and with La Nina, it doesn't come to the surface. So you have to take all these different cycles into account. And then we also have we didn't talk about it yet, but we also have the sun, which is more active at the moment within the 11-year cycle. So that also adds about 0.1 degrees Celsius to the temperature record. So yeah, it's all coming together this year.
So effectively, the response time scale is months to a few years to any shock in the marine aerosols.
Yeah, so the effect that, like, there's the direct effect which will take a few days.
A few days.
Because it washes out of the atmosphere. Yeah. So, but it's a bigger, like I already gave a long answer, of course, but it's quite a long answer because, especially over the oceans, it's different from the land. If you reduce aerosols over the land, then of course there's more other aerosol emissions over land, both natural and anthropogenic, and then you have to take that into account. But there's also the land heats very fast because it doesn't. Of course, the ocean has a very high heat capacity, but if you heat the surface of the land, it heats up fast and it starts radiating heat back fast to space. So then there's a faster energy imbalance responds faster to a forcing change. And then over the ocean, it will take much longer. And it also means that there's much more heat accumulating. So the energy imbalance is much more affected by aerosol changes over the oceans than over land. So, yeah.
Okay, thank you, Leon. And Richard, I'm gonna hold off on your question because I want to get back to the paper. I've been here for a couple hours now, and I want to make sure we get through the paper, and then we'll continue with discussion. Leon, you're welcome to interrupt at any time if you have comments on anything I'm reading here, since you were a co-author of this paper. So now we talked about the impacts, and now we're getting to scientists' warning recommendations. That sounds pretty important. So let's talk about that. I'm going to read from the paper. Motivated by recent events and trends, we continue to issue specific warnings and recommendations involving topics ranging from food security to climate justice. Coordinated efforts in each of these areas could help to support a broader agenda focused on holistic and equitable climate policy. So now they get into specific areas. Economics. Economic growth, as it is conventionally pursued, is unlikely to allow us to achieve our social, climate, and biodiversity goals. The fundamental challenge lies in the difficulty of decoupling economic growth from harmful environmental impacts. Although technological advancements and efficiency improvements can contribute to some degree of decoupling, they often fall short in mitigating the overall ecological footprint of economic activities. The impacts vary greatly by wealth. In 2019, the top 10% of emitters were responsible for 48% of global emissions, whereas the bottom 50% were responsible for just 12%. We therefore need to change our economy to a system that supports meeting basic needs for all people instead of excessive consumption by the wealthy. And then there's a bunch of pictures here talking about things, but I'm going to move over that to continue into the recommendations. You can see that in the paper with various links to see it. Stopping warming. The elevated rates of climate disasters and other impacts that we are presently seeing are largely a consequence of historical and ongoing greenhouse gas emissions. To mitigate these past emissions and stop global warming, efforts must be directed towards eliminating emissions from fossil fuels and land use change, and increasing carbon sequestration with nature-based climate solutions. However, it is crucial to explore other possible strategies to efficiently remove additional carbon dioxide, which can contribute to long-term planetary cooling. Negative emissions technologies are in an early stage of development, posing uncertainties regarding their effectiveness, scalability, and environmental and societal impacts. As such, we should not rely on unproven carbon removal techniques, although research efforts should be accelerated, depending heavily on future large-scale carbon removal strategies. At this juncture, may create a deceptive perception of security and postpone the imperative mitigation actions that are essential to tackle climate change now. So basically saying, let's explore and develop carbon capture, but let's not rely on it and therefore just keep doing what we're doing and continue emitting like we're emitting, thinking, someday we'll figure out how to get rid of it. First of all, even though we probably will figure out how to get rid of it, it'll be far more expensive to get rid of it than to not put it up there in the first place. Plus, you'll have all the damage in the meantime between the time you emit it and the time you finally get rid of it. So there's no excuse for continuing to doing what we're doing. That's my editorial comment, by the way, not in the paper. Stopping coal consumption. Back to the paper. In addition to its destructive effects on ecosystems and global health, coal accounts for more than 80% of carbon dioxide added to the atmosphere since 1870, and roughly 40% of current carbon dioxide emissions. As of 2022, global coal consumption is near record levels. In 2021, coal-related carbon dioxide emissions were greatest in China, followed by India and the United States. Coal usage in China has accelerated rapidly in the past decades, and the country now still produces nearly a third of all fossil fuel carbon dioxide and methane emissions. Eli disappeared there, but now he's back. Emissions. In response to the situation, we support the Powering Past Coal Alliance and recommend the adoption of the International Coal Elimination Treaty to phase out coal, and more broadly, the Fossil Fuel Non-Proliferation Treaty. These treaties could provide support for less wealthy countries in transitioning away from coal and other fossil fuels, including funding to build out renewable energy capacity and retrain and transition workers from the fossil fuel industry. Feedback loops, which is something we talked briefly about earlier. Climate feedback loops directly affect the relationship between emissions and warming. For example, warming causes permafrost soils to thaw, emitting methane and carbon dioxide that result in further warming. As such, reinforcing feedback loops amplify the effects of greenhouse gas emissions, leading to additional warming. Therefore, understanding feedback loops and their interactions can inform climate mitigation and adaptation strategies. Despite their importance, the combination of multiple amplifying feedback loops are not well understood, and the potential strengths of some dangerous climate feedback loops are still highly uncertain. Because of this uncertainty, we call for an Intergovernmental Panel on Climate Change special report that focuses on the perilous climate feedback loops, tipping points, and, just as a precaution, the possible but less likely scenario of runaway or apocalyptic climate change. That's a really important sentence there. And because even though the probability might be low for runaway climate change, it's like playing Russian roulette. You only have a small chance of blowing your brains out, but blowing your brains out is a pretty bad outcome. So if you're thinking of playing it, you should assume you're going to get the bullet. And just like that, even though the chances of runaway climate change are small, the impacts are so great that we should be taking it seriously and looking into it. That was my, again, editorial comment. Back to the paper. Food security and undernourishment. After declining for many years, the prevalence of undernourishment is now on the rise. In 2022, an estimated 735 million people face chronic hunger, an increase of roughly 122 million since 2019. This rise, which has pushed humanity far off track from achieving zero hunger by 2030, is due to multiple factors, including climate extremes, economic downturns, and armed conflict. Climate change has reduced the extent of global agriculture productivity growth. So there is danger that hunger will escalate in the absence of immediate climate action. In particular, there may be serious and underestimated future risks of synchronized harvest failures caused by increased waviness of the jet stream. Because of the growing risks of concurrent major crop losses in multiple regions of the world, adaptation-focused efforts are needed to improve crop resilience and resistance to heat, drought, and other climate stressors. A shift towards plant-based diets, veganism, particularly in wealthy countries, could improve global food security and help mitigate climate change. Continuing on with justice. The impacts of climate change are already catastrophic for many. However, these impacts are not unfolding uniformly across the entire globe. Instead, they disproportionately affect the world's most impoverished individuals, who, ironically, have had the least role in causing the issue. To achieve socioeconomic justice and universal human well-being, It is crucial to strive for a convergence in per capita resource and energy consumption worldwide. This entails working towards balanced and equitable levels of energy and resource consumption for both the global north and south. So now we reach the conclusions. So we're almost done here, but then we'll continue our discussion. Conclusions. The effects of global warming are progressively more severe, and possibilities such as a worldwide societal breakdown are feasible and dangerously underexplored. That's an incredible sentence, by the way. I'm going to read it again. The effects of global warming are progressively more severe, and possibilities such as a worldwide societal breakdown are feasible and dangerously underexplored. By the end of this century, an estimated 3 to 6 billion individuals, approximately 1/3 to 1/2 of the global population, might find themselves confined beyond the livable region, encountering severe heat, limited food availability, and elevated mortality rates because of the effects of climate change. Big problems need big solutions. Therefore, we must shift our perspective on the climate emergency from being just an isolated environmental issue to a systemic existential threat. Although global heating is devastating, it represents only one aspect of the escalating and interconnected environmental crisis we are facing. For example, biodiversity loss, fresh water scarcity, pandemics. We need policies that target the underlying issues of ecological overshoot, where the human demand on Earth's resources results in overexploitation of our planet and biodiversity decline. As long as humanity continues to exert extreme pressure on the Earth, any attempted climate-only solutions will only redistribute this pressure. To address the overexploitation of the planet, we challenge the prevailing notion of endless growth and overconsumption by rich countries and individuals as unsustainable and unjust. Instead, we advocate for reducing resource overconsumption, reducing, reusing, and recycling waste in a more circular economy, and prioritizing human flourishing and sustainability. We emphasize climate justice and fair distribution of the costs and benefits of climate action, particularly for vulnerable communities. We call for a transformation of the global economy to prioritize human well-being and to provide for a far more equitable distribution of resources. We also call to stabilize and gradually decrease the human population with gender justice through voluntary planning and by supporting women's and girls' education and rights, which reduces fertility rates and raises the standard of living. These environmentally conscious and social equitable strategies necessitate far-reaching and holistic transformations in the long run and could be achieved through gradual but significant steps in the short term. As scientists, we are increasingly being asked to tell the public the truth about the crisis we face in simple and direct terms. The truth is that we are shocked by the ferocity and the extreme weather events in 2023. We are afraid of the uncharted territory that we have now entered. Conditions are going to get very distressing and potentially unmanageable for large regions of the world, with the 2.6 Celsius warming expected over the course of the century, even if the self-proposed national emissions reduction commitments of the Paris Agreement are met. We warn of potential collapse of natural and socio-economic systems in such a world where we face unbearable heat, frequent extreme weather events, food and fresh water shortages, rising seas, more emerging diseases, and increased social unrest and geopolitical conflict. Massive suffering due to climate change is already here, and we have now exceeded many safe and just Earth system boundaries, imperiling stability and life support systems. As we will soon bear witness to failing to meet the Paris Agreement's aspirational 1.5 C goal, the significance of immediately curbing fossil fuel use and preventing every further 0.1 C increase in future global heating cannot be overstated. Rather than focusing only on carbon reduction and climate change, addressing the underlying issue of ecological overshoot will give us our best shot at surviving these challenges in the long run. This is our moment to make a profound difference for all life on Earth, and we must embrace it with an unwavering courage and determination to create a legacy of change that will stand the test of time. So there you go. That's about as powerful writing in a scientific paper that you will ever see. And so thank you, Leon, for being part of that paper. And it really does a great job of summarizing in plain language, not scientific speak, not scientific jargon, what's happening, that the fact that things are happening rapidly now and the scientists are scared of what's happening. And they're scared and they know what's going on. If they're scared, you should be scared too. And not scared just to be scared, but scared to drive action. Because fear is a big motivator for humans. You see the Conservative Party in the United States use fear all the time. It's, you know, a lot of times it's fake things to be scared about, like losing your gas stove or losing your SUV. But they use it all the time because it does motivate people. And we should be motivated. And we're unfortunately not enough at all. Why don't we go to Richard? Richard, you had your hand up for a long time. What's your question or comment? And then we'll see if Leon has any further comments.
Okay, I'm just going to speak my question. Thank you for this presentation. This room is always fascinating. You guys, I appreciate you so much. Full disclosure, the question I'm asking, I am a student, I'm a futurist. It is an avocation. I have published several articles on the future and have my opinions are affected by that feature of my mind. So I have a couple questions to ask of you guys, and please ignore them if they just seem totally ridiculous. First, as a preface, as far as extinction events go, the big three in my mind would be obviously Neil deGrasse Tyson's asteroid, along with climate change here, Neil deGrasse Tyson's asteroid, and obviously the caldera in Wyoming at Yellowstone, which is a looming, overdue super volcano. These are, in my sight, the major extinction events facing humanity at this time. With regards to climate change,
wait, stop. There's another one, and that was something that happened 250, actually multiple times, but the big one 252 million years ago, when CO2 from natural sources, from like volcanoes, over a very long period of time, like tens of thousands of years, built up and increased temperatures by 6 to 8 degrees Celsius, which the paper next week that Leon's a co-author of will say is possible if we maintain our current forcing. That led to 90% of all life on Earth perishing. And that probability of that happening now is much higher than the other things you mentioned.
I agree. I'm just mentioning all of the extinction events on my mind at the moment. I'm sure there may be others. The question I have, and I want to address the CO2 situation. I have two questions. The first question would be, as I said, I have written articles about an article literally entitled "From the Carbon Age to the Solar Age." I'm a believer that as a species, we are going to, as Michio Kaku suggests, we are going to occupy the solar system. We are going to occupy Mars for sure, because there's a lot of water on it. As a species, we are going to get out into the solar system, and that will be a goal of our species. Having said that, we won't be able to do it if we've destroyed ourselves on Earth.
Correct.
We just won't. But my question is more back to the real time situation. Number one, this question is real. What can current producers of fossil fuels, aside from just stopping doing what they're doing, as I understand it, I heard the the CEO of Occidental Petroleum, who is at current times in their drilling, they are returning as much CO2 to the earth through technology as they are extracting. I realize this is not.
No, that's not true.
This is kind of bullshit. I understand. I'm just saying. I'm just other than just stopping what they're doing, converting the use of fossil fuels to other purposes, like whatever construction materials, or just nothing. Do nothing. Don't touch it anymore. What are the options available to the industry? Is that what you're putting up here now?
Yeah. This is my 20-point global climate action plan.
Okay.
So, what can fossil fuel industry do? I mean, it reminds me of the line from the Gandhi movie when Gandhi had these nonviolent protests all over India, and it got the British so concerned, and they didn't really know what to do. And they went to him and says, "What do you want me to do? What do you want us to do?" The British commander said to him, and he said, "We want you to leave." So when you ask, what should the fossil fuel industry do? First of all, stop disinformation and the propaganda that they're putting forward. And they knew back in the 1960s, their own scientists said that continued emissions of fossil fuels would result in catastrophe. They used the word catastrophe or catastrophic, and they estimated the temperature today based on emissions, and they got it within 0.1 degrees. So they knew back then. So what do we have to do? They have to transform themselves into energy companies from fossil fuel companies. And BP, by the way, to their credit, yesterday or so announced they're buying $100 million worth of Tesla superchargers to put in their own supercharging network, so at gas stations. So they realize that their EVs are coming, and so they better switch over, and provide charging for that. So, but there's a lot more to do. They could buy renewable energy, and they could phase out fossil fuels. We have to phase out rather than pressuring governments to continue it and all of that. So that's asking specifically, what should fossil fuel companies do? I don't expect fossil fuel companies on their own initiative to decide to go out of business of providing fossil fuels. What we need is, the question isn't what should fossil fuel companies do? The question is, what should politicians do? And that's what this list is for. This is what politicians should do. We shouldn't ask what we're doing today, and it's kind of ridiculous, but we're asking the fossil fuel companies to pretty please, could you reduce your emissions? That's essentially what we do. And that's a stupid approach to the problem. If your world is under threat, and the threat is because we're burning fossil fuels, the obvious thing to do is to require, not ask, but require the reduction in fossil fuels at a urgent and dramatic rate. So yeah, you can't shut off fossil fuels tomorrow. People would starve, people would freeze, sure, I get that. But there's no reason why we can't phase out all new ICE cars by 2030. It'll save people money too, by the way. All of these things save a tremendous amount of money. Phase out fossil fuel electricity production by 2035. Certainly could be done. Again, renewable energy is cheaper. So it's not going to cost money. It's going to save money. And then get rid of all fossil fuel energy production by 2040. That's a hard one, but it can be done, especially if we require it. You require it. Right now we promote renewables, but we don't have to promote renewables. Just phase out fossil fuels. Renewables will take their place. So anyway, that's I'll leave that list up here. But Leon, by the way, thank you again so much for helping with that article. And is there anything?
Can I just? Leon wasn't in the room when I offered my the only improvement I would say is, and so it remains more evergreen, would be to have the burning to either have. So right now it just says Canada, and so so much of Canada is burnt that I don't know how much will burn next year. So to have it on more of a global scale,
but they did. They do. I read that part. So it's in the text. It talks about forests, and it talks about the global amount. It talks about Canada as an example because I think it's such a crazy example. But but it also talked about the global level of
just seeing that, because I don't think that was one of the graphs. I don't know, would be helpful.
It does say that here. For example, historical okay. Where is it? Global, well, you talk about global tree cover loss rates declined 9.7%. So anyway, so it is in there, but I think, but Canada is put in there because it's such a crazy thing to see. I mean, it's insane. What, 3 times more than ever before? Again, most records are usually broken by a tiny bit.
Until next year, when there's another one that will get broken.
Yeah, but the temperature record was broken by 0.5 degree. The last difference between a record and the previous record was 0.9. So 5 times more, a bigger jump, 5 times the previous largest jump. That's crazy. That's really crazy. So anyway, Leon, do you have anything to tell us about the paper coming out next week on global warming in the pipeline? Like how we should, look at it, what we should, how we should read it?
First, let me thank you for covering this paper. Great paper. And I also want to mention Saleemul Huq, who passed away yesterday, was a co-author of the paper.
I mentioned that at the beginning of the room, yes.
Yeah, sorry, I wasn't there, but so that it's quite a sad day. He passed away from a heart attack, and he was last year he was Nature called him one of the top 10 climate scientists of the world. And he was a great man, especially focusing on. He was from Bangladesh, and of course he was important voice of the developing countries and the climate change, which they have been affected with already for a longer time. They've been seeing the effects more clearly. Yes, they needed a very strong scientific voice, and it's very sad that he passed away. But thank you for covering this paper. It's indeed it's a paper showing more to translate everything that's been happening in the past year in a clear, both scientifically and in an understandable language for a broader audience. And I think the question on the Canadian fires which added about 2 billion billion tons of CO2 to the atmosphere. I think that it just shows how extreme these anomalies are, and we could also show that's more from the recent, more recent. So we didn't include in the paper yet, but we could also include a graph of, for example, the ocean temperatures and the effect on the coral reefs around Florida, for example, which would look very similar to the graph of the Canadian forest fire. So there's really and then of course we had this enormous hurricane develop, Category 5 hurricane developed within 12 hours. So there's a lot of crazy weather events which are not even mentioned in this paper because they just happened right now, and the next month, as El Nino is strengthening still, and it will take a few months for the effect of El Nino to translate into atmospheric temperatures. We can expect much more extreme weather in the months to come.
I would urge you, like in further updates like this, to really emphasize coral reefs, because just with the stuff that was projected a year or two ago,
The expectation was that we would lose 90% of coral reefs before mid-century, and that is what supports about, or what would be lost supports about 40% of animal life in the ocean. And that's like synchronized crop failures year after year after year.
Yeah. Yeah. It's an important part of the ecosystems, of course.
Hey, Leon, on this program before, you took an estimate you mentioned an estimate of what you thought the global temperature would be next year. You want to have any thoughts on that? I think you said 1.7 to 1.8 next year, global average.
I think I said 1.8 for the 12-month mean. So that was as I keep saying, it's not a prediction unless it comes true. as a sort of a joke, but
yeah. Well, it's hard. They say it's hard to make predictions, especially about the future.
Exactly, and
right.
But it's like very few people thought this year we would reach 1.5, and I was wondering whether it would, with all these, just looking at the energy imbalance and understanding the forcing changes, and now it's at least in the Berkeley Earth. That's a bit higher than the others, but they show that 2023 could reach 1.5, and
right, and that's with the first half of the year being relatively cool. I mean, not cool, but relatively cool.
The first half of the year was still influenced by La Nina,
right?
But of course now
that's amazing that we could hit 1.5 in a year that has 6 months of it still affected by La Nina. That's crazy. Maybe you can clarify something, which I thought was really interesting, that Jim Hansen had in his newsletter. I think you were part of this newsletter too, where he said that next year might be, I think he said 1.6, 1.7. But he said when El Nino goes away, the temperature is only going to drop by 0.2 or 0.3. And that means, and I think he used the phrase, for all practical purposes. He said, if it's true, I mean, he was saying, if it's true that we hit 1.6, 1.7 next year, which you're saying you think it could be even higher. He said, if that happens, and El Nino going away only means a 0.2, 0.3 drop, that means for all practical purposes, we are at 1.5 degrees trend. Because, I mean, we should say this, when people say the Paris Agreement says don't go over 1.5, they don't mean in a single year. They mean sort of the average trend line. Like, because El Nino's, it's above the trend line, La Nina's below, and they're saying the in-between level shouldn't hit 1.5. But Hansen was saying that if we're that high next year, well, then the underlying trend line is 1.5. And we've really gone up a tremendous amount. Do you agree with my interpretation of what Hansen said there?
Yeah, that's what my name is on the letter, so we've looked at that, and it's indeed like I also wrote somewhere else that if we reach this 1.5 now already in 2023, and next year will be even warmer because El Nino is still developing and will impact 2024 more. And yeah, of course, then there will be some. There might even, depending a bit on the data set, right? So there might in the Berkeley Earth, which is the higher one, which I just meant, we might even not go below 1.5. Of course, we might, but if
might be ever again, like ever again is what you mean.
That's
right?
possible because looking at the energy imbalance, that's what, for example, September and August, were record warm. September was 0.5 degree warmer than any September before, and then we look at the satellite data, and we see that there's more outgoing heat radiation, which you might think, okay, that means that more heat is relatively going out, so the energy imbalance will decrease. But this was compensated by the record high amount of absorbed solar radiation. So the albedo of the planet is keeps decreasing. And that's also that's of course with decreasing sea ice and with decreasing snow cover, and with as the Earth warms, there's also the decreases cloud cover. In the Netherlands, we know that quite well because in the summer there's much less cloud cover. In the winter, there's much more cloud cover because there's more the clouds condensate quicker. But then if it's warmer, then the cloud there's a that also reduces cloud cover together with the effect of aerosols. And then the so that's a aerosol cloud, or that's a cloud feedback. So there's aerosol cloud interaction changes, and there's a warming feedback, and then there's more warming, and that decreases cloud cover even more. So that's also part of could cause runaway effects if this effect is strong enough, and we don't know. We are just finding out.
And so we should emphasize 2 points. I mean, you did say may not drop below 1.5 ever again. That's, if that were, the trajectory that we're on, that's assuming that we don't adopt sunlight reflection methods, SRM, to interrupt that. Number one, because if we do, we can, all of the models that talk about commitment to whatever level of climate change assume that we don't adopt SRM or carbon dioxide removal.
Or that we don't start a war, or that we don't start a nuclear war, or that we don't have a super volcano. Indeed, that's what we assume. Yeah, I think that's indeed that's what. If we talk about that within the next decade, we will not go down 1.5, or we could not. Yeah, but I don't think we'll do solar radiation, solar reflection methods, or whatever you call it, in the intentionally, because we are of course doing it unintentionally.
We have to start thinking about it, but also
but we are or people are starting to think about it. But
I actually disagree with that. I think we are going to do it because the public is going to be up in arms about it.
If you don't let me finish my sentence,
sorry.
So I don't think the world will be. They could, but I don't think the world will do it within the next decade. Potentially, when the crazy weather effects take shape in the years to come, the sulfur might be put back into the shipping fuel. But I think if you would just do that without addressing greenhouse gas emissions, then we're just making the problem worse for the long run.
Yeah, of course.
Well, strongly agree with that, and I've always said that SRM is not an excuse to continue emitting fossil fuels or to not do carbon dioxide removal, because the carbon dioxide that's in the atmosphere is already acidifying the ocean. And again, that is an ecological catastrophe unfolding without attracting sufficient attention from people.
Yeah, together with the warming and the reduction in oxygen in the oceans. So the oceans are really affected, and with the plastic and with overfishing. So we're trying a lot through many ways to destroy the life in the oceans.
Right, we're trying as hard as we can. I actually think that there's an alternative way that things could play out. First of all, as you are pointing out in this paper, the world is seeing, really for the first time, the craziness of climate change, these extreme, very damaging things. And they're going to really accelerate probably next year, with even warmer temperatures. It's going to be a bad situation.
They accelerated this week already with the super hurricane.
Yeah, that was crazy too. So now the public will go from being apathetic about climate change to demanding action. And the only thing that will change the outcome in any time frame that the public will notice is SRM. I mean, you can do reductions in emissions, you can do carbon dioxide removal. None of that will change the near-term outcome of the crazy weather, of the 1.5 plus degree temperatures, it won't change any of that for decades.
Yeah, it's the other way around even, because if people would take this more seriously and we would rapidly reduce like coal-fired power plants around the world.
Yeah. Temperature go up. The temperature would go up.
Temperature would go up first, and then that's what I mean with the 1.5. I didn't finish my sentence there either. But so if we wouldn't go down below 1.5 or much, like even if we would go a little, doesn't really matter that much, of course.
Right.
If it depends on the data set, but if the temperature wouldn't dip down much below this year, right? Where it doesn't matter which data set you use, but whichever data set, if this was like becomes an average year, or the minimum year more, and so every year will be worse almost. So all these extremes which we have seen this year and which we will see in the next 2 months of this year will be like one of the better years on average, right? So
I think 2022 was the coolest year forevermore.
One way to look at it.
2022, the coolest year.
But that was quite
ever
cool.
see again until we do solar radiation management.
Yeah, but it was quite cool. So maybe even 2016 was 2020. Yeah, this 2020 was like not a La Nina year, so we're just starting.
But
well, just real quick. Also, we have to like push the point that the sooner we start doing this, the less of the permanent damage occurs. In other words, we can avoid going over tipping elements that will keep temperatures or radiative forcing at a certain level, right?
We might.
I mean, things like the methane emissions from permafrost and permafrost loss and reduced albedo. Those things are hard to get back once they happen for in general. And
that's the comparison with so if also that's with the question of the shipping emissions. So just I have this hypothesis that also contributes to the reduction in Antarctic sea ice, because there's less heat flowing from south to the north, both through the ocean and the atmosphere, because there's more being absorbed in the North Atlantic, the reductions of aerosols. That heat stays in the southern hemisphere and keeps the Antarctic sea ice from growing and increases the melt. And then if you have 1 million square kilometers less sea ice, or 2 million, if you look at the average over the past 20 years, that's a lot less reflective ice. And like if you would want to compensate for that, it's hard to imagine 2 million square kilometers of ice and how to compensate. People are talking about how many roofs but you would need you cannot count all. Even if you would paint all the roofs in the world white, I don't think you could compensate for that loss in sea ice. So we would really need to think of the orders of magnitude. They need to line up with the reality, right?
Yeah, well, part of the reality is the spatial distribution, and even if you did come up with 2 million square kilometers of rooftops, they're not going to prevent further sea ice loss at the poles.
Yeah.
By the way, exactly. back to the solar radiation management. There's one other point I was making, besides the fact that SRM is the only way to satisfy a public that is up in arms against climate change and want politicians to do something to fix it. That's the only thing that could happen quickly. But there's another thing, and that is, as you mentioned also, about AMOC collapse. That's something projected to happen anytime, but maybe 20 to 30 years from now. And that would be the mother of all tipping points, as I put it. And it's irreversible once it happens. And as far as I know, and maybe you have some thoughts on this, the only possible way to stop that from collapsing, and it may not work, but still the only possible way is to start SRM soon to try to prevent the freshwater flow of fresh water from melting Greenland, and by cooling the poles and stopping that from happening. Do you have thoughts on that? First of all, do you think that's a correct statement, that that's the only thing in our control that could slow down or prevent an AMOC collapse?
Yeah, so I don't know of any study about it, except for what I already talked about, that aerosols increase the AMOC, especially over the North Atlantic.
They help. Increased aerosols help stabilize the AMOC. Is that a?
Oh no, they increase, if reducing or increasing aerosols over the northern hemisphere increases the AMOC and
AMOC flow, which is good. That's the good thing. We want the AMOC to continue. We don't want it to slow down.
Right. Yeah, so or we decrease the slowdown. That's more accurate statement, of course.
Decrease the slowdown, yeah. But if we actually refroze the Arctic and stopped Greenland from melting, because we really not just put up a little bit of aerosols, but put up a significant amount over the poles with a purposeful, not accidental, but purposeful SRM, that would stop the freshwater. That would stop the freshwater inflow. Go ahead.
It shouldn't be black carbon, depending on the aerosols, of course.
Right. Well, actually, that's interesting. I don't know. Does sulfur particles, when they fall down out of the sky, do they cause?
I guess white or yellow, but it's more about. So you have these aerosols, but they act as condensation nuclei
for clouds. That's correct. Yeah.
And then certain aerosols act as more as a condensation nuclei for water, and other for ice crystals, and a sulfur is better condensation nuclei for ice crystals. So then you have more snowflakes instead of a yellow deposition of sulfur. So that's more. Of course, you need snow instead of aerosol deposition.
Yeah,
and inside the snowflake there will be a condensation.
A big difference between doing SRM on. By the way, we're kind of getting off topic from your paper, but talking about SRM. But a big difference is that SRM done on purpose is done in the stratosphere, where the sulfur particles last for a year or so. But when they're emitted from ships and coal plants, they last for a week or so. And so therefore
it depends on your sunlight reflection method.
Yeah, absolutely. But I'm saying just in general, doing it on purpose in the stratosphere, the much less sulfur pollution will cause more cooling. However, as you just pointed out, in the lower atmosphere, not only do the particles reflect the sun themselves, but they also help create clouds. And this was mentioned in the article, I think, in the letter. It makes brighter clouds and longer lasting clouds. So that has to be compensated. So it's not simply the 50-to-1 ratio because it's up higher in the sky. It lasts longer in the stratosphere, but it has less cooling because of the cloud effect. So you do need a little more, but still it's much less. I think it's 5 to 10% of the current pollution, if put in the stratosphere, would have more cooling effect because it lasts so much longer. So that means less pollution, less damage, less stuff on the snow. I mean, all of those. So doing it purposefully is a smarter solution.
Still, right?
Well, I'm not sure what you mean by hypothetical. It's a plan, right? That's stratospheric aerosol injection. That's people are working on how would we go about doing that. But of course, we don't know. We don't know the details yet.
You were talking about the ocean current, right? And how we could stop that, and then.
Oh, that's theoretical. Yeah, I agree. Yeah.
And then where do you emit these particles, and how high or over the ocean, which area over the ocean? It's all hypothetical, and I agree. If you want to keep the AMOC from shutting down, we should really start having the conversation about how that's even possible. And then you would also need to have these discussions. And I think it's some are still worrying about even having these discussions. But
that's right.
This, and we also don't really touch upon it in this paper. But yeah, if you want to reduce the emission, if you want to reduce cooling, that's what you need in a way. That's the only way you can do it.
Yeah, I'm going to say, by the way, that's the only way I am aware of that possibly could do it. It doesn't mean that if we did it, that it would stop it.
Yeah.
But certainly just reducing emissions and doing carbon dioxide removal, that can't stop it because its time frame is much longer than the shutdown time frame. Right? The shutdown time frame is 20, 30 years. I mean, it would be a good thing. It might help a little bit. But if you're facing a shutdown in 20 to 30 years because of Greenland melting, reducing emissions is not going to slow down the Greenland melting. I'm sorry, it will slow down the increase in Greenland melting. It'll hopefully slow the rate of increase, but it's not going to make Greenland decrease its melt.
It's still increase. So like reducing emissions. So we have to be clear, right, about reality. We can. I think it's often we go to these hypotheticals where we say, okay, if we just reduce greenhouse gas emissions to zero within a decade, but that's not happening.
Correct.
So we have to. I think I personally I like to talk only about reality. We living in a real world. We can discuss, but when we discuss those hypothetical scenarios, which are completely hypothetical, we should always be very clear about that. But we're talking about reality. We know that the greenhouse gas forcing will increase, so the warming will increase. If the warming will increase, the slowdown of the AMOC will happen faster. It's already slowing down, but the slowdown will increase as well. And then with this decrease of aerosols, which is not hypothetical, it has happened already.
Correct.
We have reduced these sulfur emissions already. The slowdown will also happen even faster. So we see the slowdown of the AMOC happening faster and faster. We will see it. It's based on the theory and also based on the modeling. We see it, we expect it, and we see it happening, and we will expect it if you take into the account the scenario, the real scenario, which is not most models don't, of including the reducing these aerosols of the ocean as well. It will happen even faster by theory, right?
So the International Maritime Organization could end up being like the evil, like, in a James Bond film, you have the evil guy that wants to destroy the world. Whoever would have thought it was the International Maritime Organization trying to clean up pollution ended up being the evil mastermind of the world.
Well, they're not the evil mastermind. I mean, it's more like we as intelligent beings are just like the Marx Brothers, stumbling over each other in comedic fashion. Tripping and falling and whatever else, trying to do the right thing.
The law of unintended consequences.
Exactly.
But no, it's worse. It's really the inconvenient truth within climate science. I've seen it really that often if you see the fine print in the studies where they look, because they compare the health effects with the environmental effects and the warming effects of reducing these aerosols, and then they take the assumption, they assume that the warming, the effects which cause the warming, or the effect that causes cooling initially, they assume that's they take the lowest assumption, so the least cooling, and then they say, okay, so there's not much warming of reducing these particles, because of the health effects, because they focus more on the health effects.
Right.
And they say, okay, it's a good thing to do this, but it's not an honest. And I'm not saying they are dishonest, but I think they are also not honest towards themselves when they do this study in like this, because it's not representative of reality.
Mm-hmm.
Or they should
and they don't take the health effects of an AMOC collapse into account either, which lowers rainfall across the entire northern hemisphere and causes several meters of sea level rise and
shifting of the monsoon systems. Yes.
Monsoons, the dieback of the Amazon. I mean, they don't take that health effect into account. They just looked at the near term effect of the sulfur pollution on people. Which is still real, by the way. It's serious. It's still serious.
Indeed, and it's serious, and I don't want to devalue the health effects. I'm working on in Ethiopia on reducing the health effects of exposure to aerosols, which kills globally 4 million women and children from biomass cooking. So I know the importance of these health effects of aerosols, and I value that, but I don't think it's right to neglect or value the warming effect of changing these emissions, because we have a duty. That's also what we discuss in this paper, which we're discussing now. We have the duty to communicate this honestly and clearly. We cannot keep silent or not model or not even mention these aerosols and or the effect of changing these aerosols, and because of the effects could be very dire. And then and even like AMOC is extreme, and it's maybe it's possible that it will happen, but even regionally. We need to know that what the potential effect of this is. We cannot ignore it, because otherwise, if we don't know, we cannot prepare. We cannot reduce the suffering which will come from it, right?
Mm-hmm.
It's not.
But I do think that we can be intelligent about it. So you're saying, by the way, the only solar radiation management that society will allow today is the accidental kind. Right? It's doing it from ships because ships are going anyway, and you probably could sneak back in the sulfur in the ship fuel, and still people would see that primarily as shipping, not as climate control. So they'll allow it. But if you did it as climate control by putting airplanes, for example, that flew up to the stratosphere and released it, again, much less pollution, much less of the health effects that are currently a problem, with much more cooling and more controlled cooling, that to me sounds like a good thing. That doesn't mean that there aren't side effects. Just by the way, there were side effects from the ship pollution, killing people, health effects. That's a side effect. But the side effects of not doing SRM, to me, seem like they will be an order of magnitude more than the side effects of doing it. And again, rather than doing ships haphazardly, let's do it more intelligently.
It's not rational.
Yeah, none of it's rational. None of it's rational.
Not rational cost-benefit analysis, and there's many subjects like that. If you even talk about it, people put you in this corner, and you say, okay, like the cost-benefit analysis of nuclear or genetically modified crops or geoengineering, and there's quite a lot of subjects similar to this.
Ask me about self-driving cars.
So
but one thing I'm wondering, it would be an interesting comparison to say, because I absolutely agree with you. We were looking at one dimension of the health effects in terms of replacing or improving the fuel in the shipping, but it was only from the immediate pollution, not any of these after climate effects that are happening rapidly. Is there something? It's like, okay, here is when the world was, using that shipping fuel, here were the climate or here were the climate effects and the human life effects. Here it is, the trajectory, the impact of those effects, not using the fuel. Here is, so do we bring it back, or here is SRM and what the multidimensional health impacts are,
Well,
so we can make a more
this study has
intelligent.
not been done.
Yeah, Leon's been the one writing these studies and talking about that for a couple of years now. And I don't know, the world
So
is
that's
not
next.
By the way, we're reaching 12:59. I want to end the room. 3 hours is probably enough, but I want to ask Leon one question on the way out. And what's your thoughts on, we talked about the temperature being 1.5, 1.6, 1.7, 1.8 next year. We also, then the next milestone is 2, which it generally is, I think Jim Hansen says, we're going to hit that in the 2040s. Do you think we might hit 2 degrees maybe for our first time this decade? And do you think that we might hit the trend line in the 2030s? What's your thought on 2 degrees of warming? A short answer, because we try to, if you have one, if you don't have a thought.
It depends on when the next strong El Nino happens, of course. And so, yeah, it's anyone's guess. With the current energy imbalance, if it's maintained, yeah, I wouldn't be surprised if that happens this decade.
Wow. Okay.
But yeah, that's just, yeah. We already see that. We will see it probably some monthly.
On a monthly basis.
Sorry?
Yeah, on a monthly basis rather than a yearly basis, you're saying?
Yeah, maybe if in January, February, we might already see a 2 degree month, 2 or 2.1.
Wow.
But that's just 1 month. But that's what. But it's also, that's already with these months in the past month of September and this month also, where we have like 1.6 or 1.7, and yeah, we're just starting to see what that means, and we don't know. For example, there's so many uncertainties, right? What will happen next with the Antarctic sea ice this year? When it's starting already with much thinner sea ice and 1 million square kilometers of sea ice missing. If you just look at the heat and calculate the heat, there's so much heat being absorbed by these oceans, which will be available to melt even more ice, that could cause already a lot of additional warming, and that would add to the energy imbalance, and then that results, of course, in more warming. So, yeah. So the next year, I said 1.8, but or the thing that's 12-month average, we don't know. It could go up even higher.
Wow. Well, it is going higher, that's for sure. But I mean, hitting that milestone so soon would be. I mean, I'm always naively hoping that hitting 1.5, for example, this year
that doesn't help
action. But
because every time even I am surprised. Well, because I've been looking at this data and I've been looking at this forcing change, and I was expecting quite significant warming, and even I was surprised by September, by September breaking the record by 0.5 degree.
Yeah.
And even I was surprised by what's happening with that the energy imbalance of September is still so high, so very high, because it was record. It was that it was 0.5 degree warmer should mean that it did mean that it radiates so much more heat to space, right? So we would expect from that we would see a decrease in the energy imbalance, but we didn't see that, and that makes it. Then, if you ask me now, and just looking at this data for the past days, because it just came available from NASA, then I take that into account when I answer your question and say, okay, it could be even worse.
Well, Leon, I want to thank you, first of all, for joining our room today. Really made it that much more interesting and informative. So thank you for that. But I also really want to thank you for, first of all, taking up this line of research that no one else seems to have been looking at all, which is the impact of shipping changes and aerosols on climate. And also thank you for working on this paper that we covered today. And thank you for working on the paper we're going to see next week. We hope that you can join the discussion, because I'm pretty sure that next Sunday we'll be talking about the global warming and the pipeline peer-reviewed paper. By the way, can I just ask you this one question? Should we expect many changes from the draft version? Will it be quite a different paper, or just sort of what we saw with a modest amount of changes?
Yeah, there's been a sort of big improvement of, as Jim also wrote in the email, is also looking more in detail about at the past climate.
Mm-hmm.
And and I think which might be one of the biggest findings, which hasn't received much attention, and which is also in the paper, was already
draft.
in the paper.
Yeah,
the draft is the effect of aerosols in the past 6,000 years.
Oh, okay.
And
okay.
Because that's really important for climate science. Maybe also important for understanding what will happen in the next decades, or it is. But it's also really important to understand the climate models, which build, of course, on the reproduction of the climate in the past 6,000 years, based on the CO2 and the greenhouse gas concentrations, which are retrieved from ice core data. Mm-hmm. So it's really important to also that we show that it's very likely that at this time there was also aerosol forcing
from human. To make it clear, human aerosol forcing, right?
Yeah, human by millions of humans around the world burning trees and burning grasslands, right. and so all these big civilizations of Genghis Khan and of the Egyptians and the Roman empires and the Incas and whoever you can think of that lived at these times and who changed the surface of the planet. They also emitted a lot of particles which cooled the climate, next to increasing the greenhouse gas concentrations of CO2 starting 6,000 years ago, by deforesting the planet, and by also a bit later also increasing methane by starting to grow rice and agriculture in general. So and that's really important to understand that there's this Holocene temperature conundrum, where there's the question raised, like, why did the planet cool down while the CO2 and the greenhouse gas concentrations increased? And this helps explain that.
Certainly it explains it at the beginning of the Industrial Revolution. When we started burning coal, the temperature dropped, and that was because the smoke from the coal was much stronger than the little bit of CO2 back then. And then it kind of, through World War II, it was a trade-off between warming from CO2 and cooling from aerosols. Yeah. And then finally, in 1970s, with the Clean Air Act, the CO2 took over and it went up at a straight line. And now we've reduced the aerosols even more. And now, as you and Jim Hansen have pointed out, the climate warming has accelerated. So that's anyway, we're looking forward to your paper next week. And thank you again for this paper. This is a paper, I think the pipeline paper is certainly a much more difficult paper for many people to read and understand in the general public. The paper we talked about today is very clearly written. It's written without jargon, and it presents very kind of basic information. And it's one of the most important scientific papers there is. And we'll have to see how we can increase the exposure of this paper. By the way, I did help you get exposure for the letter you did with Jim Hansen last week, the newsletter, in preparation of the pipeline paper. I did a summary set of tweets which currently has over 80,000 views on it. So, which gave a super short summary of that letter that you did. So I'm helping get the word out there a little bit. But anyway, again, just thank you so much for everything you're doing, and we look forward to having you on again. I want to thank everybody who was here in Zoom, on Clubhouse, and on YouTube today. A recording of this room will be available on YouTube going forward, and so everyone else can continue to listen to it. That's a big advantage of this platform, but I think we still have to do some work on the platform and find a one that has a better experience for the more of a podcast type feel. So we'll continue to work on improving the platform experience. But thank you again, Leon. Thanks everyone else. We will see you. We will see you next time. Everyone, keep an eye out. Follow me on Twitter at Dan Miller 999. Leon, what is your Twitter handle?
Leon Simons 8.
Leo Simons and the number 8. And at Leon Simons, the number 8. And follow Leon so you can see the latest papers that come out. He posts really interesting stuff all the time, and it causes a lot of controversy now and then as well when he posts some of these things. And of course, follow Stacy and Eli as well. And that way you can keep track of when that paper comes out. I'll post about it, and then Leon will post about it. And anyway, thanks everyone for coming. This is Climate Chat. I'm your host, Dan Miller. We will see you next time, Sundays at 10 a.m. Pacific time. Thanks and bye-bye.